October 9th, 2024, 3:17 in the morning. In a darkened room at the National Hurricane Center in Miami, meteorologist Sarah Chen stares at numbers on her screen that violate everything she understands about atmospheric physics. The pressure inside Hurricane Milton, measured by dropsondes falling through its core, drops 18 millibars in a single hour. Not over 6 hours, which would be extraordinary. Not over 3 hours, which would shatter records. 18 millibars in 60 minutes. This shouldn't be possible. Hurricane intensification follows principles as rigid as gravity. Warm water provides energy. Rising air creates low pressure. The Coriolis effect organizes rotation. These processes take time. The atmosphere cannot reorganize itself instantaneously, any more than water can freeze in seconds. Yet Milton is rewriting rules that have governed Earth's weather systems for 4 billion years. Chen calls the duty officer. Within minutes, 6 senior meteorologists crowd around her terminal, watching the impossible unfold in real time. Hurricane hunters aircraft that fly directly into storms radio confirmation. Their onboard instruments, calibrated to within 1/10 of a millibar, show the same catastrophic pressure drop. Milton transforms from a Category 1 hurricane with winds of 90 miles per hour into a Category 5 monster with winds of 195 miles per hour in just 18 hours. The previous record for rapid intensification, set by Hurricane Wilma in 2005, was 42 hours. Milton completes the same transformation in less than half that time, but the raw numbers tell only part of the story. What meteorologists witnessed that October morning represents something fundamentally different from every hurricane in recorded history. Not just faster intensification, not merely a stronger storm. Milton exhibits behaviors that suggest atmospheric processes science has never documented, mechanisms that transform a tropical depression into a planetary-scale engine of destruction with terrifying efficiency. Aircraft Commander Major Jennifer Rodriguez guides her C-130 J Hurricane Hunter through the outer rain bands at 0400 hours. She has flown into 73 hurricanes over 12 years. She knows the signature feel of each intensity, the rhythmic turbulence of Category 2 storms, the sustained violence of Category 4 monsters, the almost smooth power of Category 5 systems whose eye walls are so organized they create stable vortices. Milton feels different. The turbulence arrives in waves that make no sense. Gravity waves, atmospheric ripples caused when air rebounds off the ocean surface, normally propagate smoothly through storm systems. Milton's gravity waves arrive chaotic, overlapping, amplifying unpredictably. The aircraft drops 200 feet in 3 seconds, then rockets upward with enough force to pin the crew to their seats. Vertical velocity at 47 meters per second, the flight meteorologist reports, voice tight with tension. That translates to 105 miles per hour air rising faster than winds in most tornadoes. The C-130 punches through the eye wall, where instruments record wind speeds accelerating from 120 to 195 miles per hour in a span of minutes, not hours. Below them, the Gulf of Mexico glows. Bioluminescent plankton, normally visible only near shore during red tides, illuminate the entire storm field. Dinoflagellates flash when agitated by wave action, creating a natural light show across thousands of square miles. The waves themselves tower to heights that ocean buoys, designed to measure seas up to 70 feet, register before their masts snap and they go silent. Rodriguez banks toward the eye, following protocol established over 7 decades of storm penetration. The eye wall, that arena of maximum winds, normally extends 20 to 30 miles in diameter. Milton's eye measures 8 miles across. When they break through into the calm center, everyone on the aircraft goes silent. The eye rises like a stadium built by gods. Clouds form walls 60,000 feet high, higher than commercial aircraft fly, higher than Mount Everest twice stacked. Stars shine through the opening at the top, impossibly distant. The air inside remains eerily calm, winds dropping to less than 10 miles per hour. But the surrounding clouds rotate so fast they blur, creating optical effects, halos, coronas, strange refractions of light that momentarily make the moon appear to orbit the storm rather than Earth. The drop sonde, a sophisticated weather instrument that parachutes through the storm core, transmits data that makes no physical sense. Ocean temperatures at the surface, 91 degrees Fahrenheit, normal for the Gulf in October, but 300 feet deep, 90 degrees, 600 feet deep, 88 degrees. The warm layer extends 3 times deeper than any storm has ever encountered. Milton found a reservoir of heat, a vast underwater battery of thermal energy, and it's consuming that energy at a rate meteorologists struggle to calculate. The storm converts heat to wind with terrifying efficiency, generating kinetic energy equivalent to 10 Hiroshima bombs every second. Not every hour, every second. Ocean buoys scattered across the Gulf of Mexico tell a story about something humanity has never witnessed at this scale. The instruments anchored platforms carrying sensors that measure temperature, salinity, wave height, and current speed begin failing at 0530 hours, not from mechanical failure. They simply exceed their design parameters and shut down. Buoy 42003, positioned directly in Milton's path, transmits its final reading at 0547. Wave height 73 feet, period 14 seconds, wind sustained at 187 miles per hour. Then, silence. These buoys cost $200,000 each and are built to survive Category 5 hurricanes. They are engineered to continue functioning in the exact conditions they're now measuring. Yet they fail not because of poor design, but because the engineers who built them never imagined conditions this extreme. The Gulf itself undergoes transformation. Satellite thermal imaging reveals something meteorologists will spend years trying to explain. The loop current, a river of warm water that flows from the Caribbean through the Gulf, normally remains confined to depths below 500 feet. But thermal sensors show warm water rising, forming massive eddies that break off from the main current and spiral toward the surface. Milton positions itself directly over one of these eddies, the storm's low pressure dropping toward 880 millibars, a number that shouldn't exist outside. Theoretical models literally sucks warm water upward. The ocean responds like water being drained from a bathtub, creating circulation patterns that reinforce the storm's rotation. Storm and ocean become coupled, each driving the other toward intensities that make previous hurricanes seem gentle by comparison. But something else happens in that coupling, something that instruments detect, but scientists struggle to interpret. The ocean beneath Milton develops distinct temperature layers that violate thermodynamic principles. Hot water should rise, cold water should sink, mixing should occur. Yet instruments detect pockets of near-boiling water 100 degrees Fahrenheit trapped beneath cooler surface layers at 70 degrees. These temperature inversions shouldn't be stable. They should collapse immediately, mixing into uniform gradients. They don't. The inversions persist for hours, feeding heat directly into the storm's core through mechanisms that remain unexplained. It's as if Milton has learned to organize not just atmosphere but ocean, creating structures in water that shouldn't exist outside laboratory conditions. The eye wall develops features that appear on radar like nothing meteorologists have seen. Within the main circulation, smaller vortices appear mesovortices, mini tornadoes spinning within the larger hurricane. This happens occasionally in strong storms. What doesn't happen is what Milton does next. The mesovortices organize. Instead of appearing randomly and dissipating, they form patterns. 6 distinct vortices arrange themselves in a ring around the eye, each spinning at 300 miles per hour, each spaced exactly the same distance from its neighbors. They carve grooves in the ocean surface, visible from space spiral patterns that look disturbingly artificial, as if drawn by some vast compass. These mesovortices act as auxiliary engines, additional circulation centers that feed energy into the main storm. They accelerate the eye wall wind speeds beyond what the storm's central pressure would normally produce. It's as if Milton has developed multiple hearts, each pumping atmospheric pressure in synchronized rhythm. The main eye wall becomes a particle accelerator for water. Droplets caught in the updrafts rise at 200 miles per hour faster than skydivers fall, faster than raindrops fall in reverse. They shoot upward with such force that they reach altitudes of 40,000 feet in minutes. At those heights, temperatures plunge to minus 60 degrees Fahrenheit. The droplets freeze instantly, but they don't fall. The updrafts are so powerful that ice crystals remain suspended, accumulating more water vapor, growing larger. Some achieve the size of golf balls before finally becoming too heavy and plummeting back toward Earth. During their descent, they enter warmer layers, melt, then get caught by updrafts and lifted again. Aircraft instruments detect hailstones that have undergone 15 freeze-thaw, cycles visible as concentric rings in their cross-sections, like tree rings recording the storm's violence. These supercooled projectiles eventually fall as rain, but rain that contains ice crystals at its core, water that remains partially frozen despite passing through warm air. The physical processes required to maintain these cycles shouldn't be possible. The energy requirements alone lifting water that high, that fast, continuously for hours, exceed what models predict hurricanes can sustain. Yet Milton sustains them. Lightning illuminates the eye wall with such frequency it becomes continuous. Not individual flashes separated by seconds, but a sustained electromagnetic storm that turns night into flickering day. Instruments aboard the Hurricane Hunter aircraft count 3,000 lightning strikes per minute, 10 times the rate of severe thunderstorms, 100 times the rate of ordinary rain. But these aren't ordinary lightning strikes. The bolts originate in the eye wall, where ice crystals collide with such violence they generate electrical charges. Positive charges accumulate at the top of the storm. Negative charges concentrate near the ocean surface. When the potential difference becomes too great, current flows lightning that carries 10 times the voltage of typical strikes. Some bolts extend horizontally for 50 miles, connecting different parts of the storm system. Others shoot upward, out of the storm entirely, reaching the stratosphere where they create Sprite's red glowing columns of plasma that exist for milliseconds. The electromagnetic field, generated by this continuous discharge, becomes detectable from the International Space Station, showing up on instruments designed to monitor Earth's magnetic field. Astronauts report seeing Milton from 250 miles altitude, a glowing spiral of light that pulses with its own rhythm. Independent of the sun or moon, the storm creates its own electromagnetic ecosystem. Radio communications within 1,000 miles of Milton Center become unreliable. GPS satellites experience interference, their signals scattered by the ionized atmosphere. Ships report compass errors of several degrees, the storm's magnetic field becoming strong enough to influence navigation instruments. Military aircraft are forced to switch to inertial guidance systems, technology normally reserved for operations in electromagnetic warfare environments. What creates magnetic fields this powerful? Current understanding suggests only planetary-scale processes, Earth's molten core, solar storms can generate fields that interfere with satellite navigation. Yet Milton, a storm system barely 200 miles across, manages to do exactly that. Below the storm, the ocean reveals its own mysteries. Sensors dropped by research vessels detect infrasound acoustic waves below the threshold of human hearing. These waves propagate through water at 1,500 meters per second, traveling thousands of miles from Milton's center. Hydrophones in the Caribbean detect them. Monitoring stations near the Galapagos record them. Some signals reach the South Atlantic, weakening but still measurable, 6,000 miles from their source. Animals respond to these infrasound waves long before the storm arrives. Dolphins flee the storm zone 72 hours before Milton forms, their pods moving north in synchronized groups despite being separated by hundreds of miles. They detect pressure changes through organs scientists don't fully understand, possibly their inner ears, possibly sensory systems that remain undiscovered. Whatever mechanism they use, it perceives atmospheric changes invisible to human instruments. Sharks exhibit similar behavior, diving to depths below 1,000 feet and remaining there until the storm passes. Seabirds, normally feeding near the surface, vanish from coastal areas 3 days before Milton makes landfall, despite clear skies and calm seas. They don't just move away from the storm's path, they flee in directions perpendicular to Milton's track, as if avoiding not just the storm itself but some larger zone of influence. The evacuation extends beyond the ocean. In Georgia, 500 miles from Milton's center, seismographs detect rhythmic pulses that match the storm's rotation period. The pulses aren't earthquakes. They're pressure waves in Earth's crust, caused by the storm's incredibly low central pressure, literally deforming the surface of the planet. The ground beneath Milton rises 3 inches, not gradually over days, but in response to the storm's passage, lifting and falling like a slow tide. GPS stations designed to measure tectonic motion register this deformation, creating data that looks identical to small earthquake precursors. Emergency systems designed to detect seismic activity issue warnings for events that never occur. Milton has become powerful enough to move continents fractionally, temporarily, but measurably. At the National Hurricane Center, the morning shift arrives to find their night shift colleagues still at their stations, unable to look away from the unfolding phenomenon. The storm, that should not exist, continues to intensify, its central pressure dropping below 880 millibars, a number that appears only in theoretical papers about mega-hurricanes on super-Earth planets with thicker atmospheres. Sarah Chen pulls up historical data, searching for precedents. She finds none. Hurricane Patricia in 2015 held the previous Western Hemisphere record, 872 millibars. Hurricane Tip in the Pacific in 1979, 870 millibars. Both storms were extraordinary, once-in-a-lifetime events that meteorologists studied for decades. Milton drops to 877 millibars and continues to intensify. The model's sophisticated computer simulations that normally, to predict hurricane behavior days in advance, fail completely. They show Milton weakening, encountering wind shear that should disrupt its circulation, moving over cooler water that should starve it of energy. The actual storm ignores every limiting factor, continuing to strengthen even as conditions deteriorate around it. It's as if Milton operates under different physical laws than previous hurricanes. The storm begins generating chemical reactions in the upper atmosphere that instruments detect but scientists struggle to explain. Ozone, normally stable at stratospheric altitudes, begins breaking down at accelerated rates. The storm's updrafts inject water vapor and ice crystals into layers that should remain bone dry. These particles catalyze reactions that destroy ozone molecules, creating temporary holes in the ozone layer directly above the hurricane. The holes persist for days after Milton passes, allowing increased ultraviolet radiation to reach the surface. Birds migrating through the region experience navigation errors, their internal compasses disrupted by atmospheric chemistry changes. Millions of birds veer hundreds of miles off course, showing up in locations they've never historically visited. The storm doesn't just affect weather, it reorganizes the chemistry of the atmosphere itself. By 0800 hours, Milton's eye wall achieves peak intensity. The storm becomes what meteorologists will later call a hypercane, a theoretical storm type that shouldn't exist on modern Earth. Winds exceed 195 miles per hour. The pressure gradient, the change in pressure from the storm's center to its outer edge, becomes so extreme that air molecules accelerate to speeds normally seen only in tornadoes. The storm creates microvacuums. In certain spots within the eye wall, air pressure drops so rapidly that seawater begins to boil at normal temperatures. Not metaphorically, actual boiling, with bubbles forming and vapor rising, despite water temperatures of only 90 degrees Fahrenheit. The phenomenon lasts only seconds at any given location, but it occurs across hundreds of square miles as the eye wall rotates. These boiling patches feed vapor directly back into the storm, creating a feedback loop. Lower pressure causes boiling. Boiling produces vapor. Vapor strengthens the storm. Stronger storm creates lower pressure. The cycle accelerates beyond any natural limits that should exist. Aircraft instruments detect temperature anomalies that make no physical sense. In the eye wall, where air rises at 200 miles per hour, temperatures should drop rapidly with altitude. Instead, instruments detect temperature inversions, layers where air becomes warmer as altitude increases. These inversions shouldn't be stable. Rising air should mix with surrounding atmosphere, equalizing temperatures. But Milton maintains these inversions for hours, creating stratified layers of atmosphere that remain separated despite violent turbulence around them. The storm has developed internal structure organization beyond simple rotation. It's building architecture in the atmosphere, creating zones with different properties, each zone supporting and reinforcing the others. Satellite gravimeters instruments designed to measure Earth's gravitational field with extraordinary precision to detect something unprecedented. Milton displaces 40 billion tons of water from ocean to atmosphere in 24 hours. This mass redistribution is large enough to affect Earth's rotation. By microseconds, imperceptible to humans, but measurable by atomic clocks synchronized to GPS satellites. The planet's rotation slows fractionally as Milton pulls water upward, concentrating mass closer to Earth's rotational axis. The effect reverses as the storm dissipates and water returns to the ocean. But for a few hours, this storm, this single weather system, influences the rotation rate of an entire planet. The implications stagger climatologists. If one storm can affect Earth's rotation, what happens when multiple Milton-class hurricanes develop simultaneously? What happens when these storms become routine rather than exceptional? The questions multiply faster than answers emerge. Deep ocean sensors detect Milton, pulling water from the loop current with such force that the current's flow temporarily reverses. The loop current normally moves water at 3 miles per hour fast for ocean currents, but nothing dramatic. Under Milton's influence, surface water accelerates to 10 miles per hour, flowing backward, creating eddies and countercurrents that won't dissipate for weeks. The storm reorganizes ocean circulation patterns that should remain stable over geological timescales. At 1400 hours, Milton's eye passes over a deep ocean monitoring station, a platform built to withstand Category 5 hurricanes and equipped with instruments that measure every parameter of sea state. The platform survives, barely, but the data it transmits during Milton's passage reveals conditions that shouldn't exist. Ocean waves reach 82 feet from trough to crest heights, normally seen only during century storms, but these waves move in directions that make no sense. Normal hurricane waves radiate outward from the storm center in spiral patterns. Milton's waves converge, moving inward toward the eye. The storm has somehow reversed wave propagation. Water flows uphill, against gravity, driven by air pressure gradients that exceed anything in historical records. The ocean surface beneath Milton's eye develops a depression, a pit in the sea measuring 12 feet deep and 5 miles across. Satellite altimeters detect this depression as the storm passes, watching water flow downward into the low-pressure void, creating a temporary valley in the ocean. Inside this valley, the normal structure of ocean layers breaks down completely. Thermocline's boundaries between water masses of different temperatures disappear. Halocline's boundaries between different salinity levels vanish. The ocean becomes vertically uniform, thoroughly mixed by forces that penetrate deeper than any storm wave should reach. Marine biologists will later discover that deep-sea fish species that normally never venture above 2,000 feet depth were found dead on the surface, pulled upward by currents that reached into the abyss. Milton doesn't just affect the surface ocean. It reaches down into depths previously untouched by atmospheric phenomena. The storm speaks a language written in isotopes. Rainwater collected from Milton's outer bands shows unusual ratios of oxygen-16 to oxygen-18 isotopes that serve as chemical fingerprints of water's origins and history. The ratios indicate that some of Milton's water vapor originated from depths below 1,000 feet, pulled from ocean layers that don't normally contribute to storm formation. Other isotope signatures match predictions for climate conditions in the year 2100. These signatures appear in Greenland ice cores, samples from periods 130,000 years ago when Earth was 2 degrees warmer than today's pre-industrial baseline. The Eemian interglacial period, a time when hippos lived in Britain and seas were 20 feet higher, experienced storms that produced identical isotope ratios. Milton carries chemical messages from both past and future. Climate scientists examining this data realize they're not witnessing an anomaly, they're witnessing a preview. The storms of the next century won't gradually increase in intensity. They'll undergo phase transitions, suddenly jumping to new intensity levels that have no modern precedent but abundant precedent in Earth's geological record. We've seen these storms before, written in ancient ice and deep-sea sediments. We're seeing them again now, and they're telling us something about the world we're creating, something profound, something urgent, something that demands we reconsider every assumption about how quickly our climate system can transform. By 1800 hours, Milton begins to weaken, not because it encounters unfavorable conditions, but because it has consumed all available fuel. The storm has extracted every joule of heat from the ocean beneath it, cooling surface water by 9 degrees Fahrenheit across a swath 200 miles wide. It has created a cold wake, a trail of chilled water that will suppress hurricane formation in the Gulf for the rest of the season. But the weakening reveals something nearly as extraordinary as the intensification. Milton doesn't gradually diminish. It collapses. In 6 hours, winds drop from 195 to 90 miles per hour, a weakening rate that breaks records just as its intensification did. The eye wall disintegrates into bands of thunderstorms. The eye itself expands from 8 miles to 40 miles in diameter, losing its organized structure. The storm transitions from hypercane to ordinary hurricane in less time than it takes most storms to cross a single state. Weather satellites capture the final phase. Time-lapse imagery shows Milton's spiral structure unwinding like a spring releasing tension. The clouds don't dissipate randomly. They peel away in organized layers, as if the storm is deconstructing itself systematically rather than simply falling apart. Even in death, Milton exhibits structure. In the days that follow, as meteorologists analyze terabytes of data, certain facts become undeniable. Milton represents not an anomaly, but a harbinger. The storm demonstrated intensification rates that models suggested were impossible with current ocean temperatures. Yet those temperatures exist now, in October 2024, not in some distant future century. The implications are clear and terrifying. If Milton-class storms can form now, what happens as oceans continue warming? What happens when the vast thermal batteries of the deep ocean, currently isolated from surface weather, become accessible to storms? What happens when the mechanisms Milton demonstrated become routine rather than exceptional? We don't know, but deeper questions remain. How did Milton organize mesovortices in perfect geometric patterns? How did it maintain temperature inversions that should collapse? How did it reverse ocean wave propagation? These aren't questions about storm intensity. They're questions about fundamental atmospheric physics. Milton operated under principles we don't understand, creating structures that shouldn't be stable, maintaining conditions that violate our models. Not because those models are wrong, but because they're incomplete. Something about hurricane physics, something essential, remains hidden from our current understanding. The storm woke something, not in the ocean or atmosphere, but in our awareness. It showed us that weather systems can achieve organization levels we thought impossible. It demonstrated that the boundary between ordinary hurricanes and hypercanes is not a smooth gradient, but a threshold, a point beyond which different rules apply. And we're approaching that threshold faster than anyone predicted. October 9th, 2024. The day we learned that monsters don't gradually emerge from changing climates. They wake suddenly, fully formed, operating on principles we're only beginning to glimpse. The question isn't whether we'll see more Miltons. The question is whether we'll understand them before they reshape our world beyond recognition. 4 billion years ago, Earth possessed no oceans, only a molten surface, cooling beneath clouds of steam that reached into space. The planet's rotation period lasted 6 hours instead of 24. Days passed in rapid succession as the young world spun like a top, shedding heat into the void. Then, water condensed. The first rains fell not as showers, but as deluges that lasted millennia. Steam became droplets, droplets became torrents, torrents carved the first river valleys into cooling rock, filling basins that would become the first seas. And with water came weather, primitive at first, chaotic, but following principles that would govern atmospheric circulation for the next 4 billion years. The earliest storms bear no resemblance to modern hurricanes. They arise from temperature gradients between day and night sides of a planet still spinning too fast for organized rotation. These proto-storms last days or weeks, dissipating as the surface beneath them cools, then reforming elsewhere. They reshape continents with rainfall, measured not in inches, but in feet per day, carving vast canyons that later ages will fill with sediment. But they don't rotate. Not yet. Earth must slow its spin before the Coriolis effect. The apparent deflection of moving objects on a rotating surface becomes strong enough to organize storm circulation. The moon, closer then than now, raises tides that drag against the seafloor, gradually breaking Earth's rotation. Each century, the day lengthens by a fraction of a second. Each millennium, that lengthening accumulates. By 3 billion years ago, the day extends to 18 hours. The Coriolis effect strengthens, and something new appears in the atmosphere, the first rotating storms, crude ancestors of modern hurricanes, spinning over warm seas in Earth's tropical zones. Fast forward 3 billion years, 12,000 years ago, Earth emerges from an ice age. Massive glaciers covering Canada and northern Europe retreat rapidly, dumping fresh water into the North Atlantic at rates that dwarf any modern river. The influx disrupts ocean circulation patterns that have remained stable for thousands of years. The Gulf Stream, that river of warm water flowing from the tropics to the Arctic, weakens, then stops entirely. Within a decade, Europe's climate shifts from temperate to Arctic. This period, the Younger Dryas, lasts 1,300 years. Global climate systems oscillate wildly between states that should be stable. Temperature records from ice cores show variations of 15 degrees Fahrenheit occurring in less than a decade, changes that normally require millennia. The atmosphere struggles to find equilibrium, overshooting and undershooting like a pendulum released from an extreme angle. During this period, storms achieve intensities that have no modern equivalent. Theoretical models suggest these transition period tempests, sometimes called hypercanes, sustained winds exceeding 500 miles per hour. They formed over oceans warmed by irregular circulation patterns, feeding on temperature gradients that were simultaneously too large and too unstable to persist. These storms lasted days, not weeks, burning through available atmospheric energy with terrifying efficiency. We have no direct observations of these storms. They occurred before human civilization developed writing, but their signatures appear in geological records: massive erosion events, sudden sediment deposits, changes in coral growth patterns that suggest waves of extraordinary height. The storms left scars in stone that remain readable 12,000 years later. Then, abruptly, they stopped. Earth's climate system found new equilibrium. Ocean circulation patterns stabilized. Temperature gradients moderated. The conditions that spawned hypercanes vanished, replaced by the familiar pattern of seasonal hurricanes that historical civilizations would learn to predict and, sometimes, survive. 8,000 years ago, in the region we now call the Caribbean, the modern hurricane emerged. Warm water check. Earth's rotation at 24 hours per day check. Temperature differences between tropical and polar regions check. All the ingredients aligned, creating conditions that would persist, with minor variations, for the next 8 millennia. Ancient civilizations living along hurricane-prone coasts developed sophisticated understanding of these storms. Mayan astronomers tracked their seasonal appearance, noting correlations with stellar positions. Taino islanders built settlements inland during hurricane season, moving to coastal areas only during calmer months. Knowledge passed through generations, encoded in stories, rituals, or architectural choices. But this knowledge remained local, fragmented. A storm devastating Jamaica might be unknown to sailors in Florida a few hundred miles away. No communication system existed to warn distant populations. Each coastal community faced hurricanes in isolation, developing their own strategies, accumulating their own hard-won wisdom through repeated disasters. The modern era of hurricane science begins in 1840, when William Redfield, a self-taught meteorologist and steamship operator, makes a radical decision. He deliberately sails into a hurricane. Armed with handheld barometers and a notebook, Redfield measures pressure, wind direction, and wave height as his ship struggles through the storm. He survives, barely, and emerges with observations that transform meteorology. Hurricanes, he demonstrates, rotate counterclockwise in the northern hemisphere. They have definable centers where pressure reaches minimum values. Wind speeds increase as ships approach these centers, then drop dramatically in the eye. Most importantly, hurricanes follow predictable patterns. They're not supernatural punishments or random chaos. They're atmospheric phenomena governed by physical laws, laws that humans can study, understand, and potentially predict. The Great Hurricane of 1780 teaches humanity the price of ignorance. The storm forms in the Atlantic, tracking west toward the Caribbean in early October. No warning system exists. Ships at sea have no means of communicating with ports. Coastal settlements receive their first indication of the hurricane when winds begin rising, by which point escape becomes impossible. The storm strikes Barbados with winds estimated at 200 miles per hour. It destroys every building on the island. Then it moves to Martinique, where storm surge 30 feet high sweeps coastal towns into the sea. St. Lucia follows, then Puerto Rico, each island suffering devastation that will require decades to repair. But the deadliest impact occurs at sea. A British fleet of warships, returning from operations in the Caribbean, encounters the hurricane north of Cuba. The fleet, 300 ships carrying thousands of sailors, attempts to ride out the storm at anchor. It's the wrong decision. The anchors drag. Ships collide with each other in the darkness and massive waves. Masts snap. Hulls breach. By morning, nearly the entire fleet has sunk or been driven ashore as wreckage. 22,000 people die in a single day. The loss reshapes Caribbean history. Britain's naval dominance in the region ends temporarily. Spain gains strategic advantage. France moves to fill the power vacuum. A storm, an atmospheric phenomenon following simple thermodynamic principles, alters the course of empire. The disaster prompts the first systematic attempts to predict hurricane tracks. If storms follow patterns, perhaps those patterns can be anticipated. Ship captains begin sharing observations with port authorities. Coastal settlements establish basic warning systems, flags, cannons, church bells, to alert populations when storms approach. But prediction remains crude. Hurricanes still arrive with minimal warning. Death tolls remain catastrophic. By the late 19th century, telegraph networks connect coastal cities, allowing hurricane warnings to propagate faster than the storms themselves. For the first time, populations in a hurricane's path might receive notice hours or even a full day before winds arrive. The advantage seems overwhelming. It isn't enough. On September 8, 1900, a Category 4 hurricane approaches Galveston, Texas. Weather Bureau forecasters issue warnings. The city receives word that a major storm is approaching from the Gulf of Mexico, but the warnings contain no information about storm surge, the dome of water pushed ahead of hurricanes that often causes more deaths than wind. Galveston sits on a barrier island barely 9 feet above sea level. As the hurricane makes landfall, surge 15 feet high sweeps across the entire island. Buildings collapse under the assault of water, moving at 30 miles per hour. Debris becomes battering rams, demolishing structures that might otherwise have survived. The island transforms into a temporary sea dotted with ruins. 8,000 people die in 6 hours. The Galveston hurricane remains the deadliest natural disaster in United States history, but it catalyzes change. In the aftermath, the Weather Bureau creates dedicated hurricane warning networks. Coastal cities construct seawalls. Building codes begin requiring elevated foundations in flood-prone areas. The science of storm surge prediction begins its slow development. Most significantly, authorities abandon the idea that warnings alone suffice. If a major hurricane approaches a vulnerable coastal area, evacuation becomes the only viable option. This principle, controversial at the time, will save countless lives in the century to follow. 1943. World War II dominates global attention, but in the skies over the Gulf of Mexico, a different kind of battle begins. Colonel Joseph Duckworth, an experienced Army Air Force pilot, hears reports of a hurricane approaching the Texas coast. Aircraft at his training base face potential destruction on the ground. His fellow pilots doubt that planes can survive flight into such storms. Duckworth decides to prove otherwise. He takes off. In a single-engine AT-6 trainer, an aircraft never designed for storm penetration, and flies directly toward the hurricane. He navigates by intuition and dead reckoning, watching the sky darken as he approaches the storm center. Turbulence intensifies. Rain reduces visibility to 0. The plane shudders through updrafts and downdrafts that threaten to tear it apart. Then, suddenly, calm. Duckworth breaks into the eye, an arena of clear air 15 miles across, surrounded by towering clouds that extend beyond his aircraft's ceiling. Sunlight streams through the opening at the top. The ocean below shows wave patterns spiraling inward toward the center. He circles twice, taking mental notes, then navigates back out through the eye wall. He lands safely, and hurricane reconnaissance is born. Within months, the military establishes dedicated hurricane hunter squadrons. Modified bombers fly into storms, dropping instruments called dropsondes that measure pressure, temperature, and humidity as they fall. The data transforms hurricane prediction. Forecasters can now determine storm intensity and track in real time rather than relying on ship reports that might be hours old. The hurricane hunters fly through every major Atlantic storm for the next 8 decades. They save thousands of lives by providing accurate warnings. They advance meteorological understanding by gathering data from within the storms themselves. And occasionally, They encounter conditions that even their specially modified aircraft cannot survive. 1969. Hurricane Camille approaches the Mississippi coast as a Category 5 storm with sustained winds of 190 miles per hour. Pressure in the storm center drops to 900 millibars, the second lowest pressure ever recorded in an Atlantic hurricane. But it's the storm surge that makes Camille legendary. Water rises 28 feet above normal levels as the storm makes landfall at Pass Christian, Mississippi. The surge doesn't arrive as a wave, but as a rapid tide, water level increasing several feet per minute until the ocean stands higher than second-story buildings. Everything below that level drowns. A group of residents in an apartment building refuses to evacuate, choosing instead to hold a hurricane party on the third floor. They believe the building will survive its concrete construction, designed to withstand extreme winds. What they don't anticipate is the surge. Water reaches the third floor. The building's foundation, undermined by scouring currents, collapses. Only one person from that party survives. Camille's storm surge sets records that stand for decades. Meteorologists study the storm for years, trying to understand how surge height relates to central pressure, forward speed, and coastal geometry. The models they develop become foundation for modern surge prediction systems. But Camille teaches another lesson. Evacuation cannot be optional. Some percentage of the population always refuses to leave, convinced their homes will protect them. Authorities begin developing mandatory evacuation protocols, enforceable by law, for extreme hurricanes. The protocols remain controversial. They also remain necessary. The technology of hurricane observation advances rapidly through the late 20th century. Weather satellites allow forecasters to track storms from formation to dissipation. Doppler radar reveals internal structure, the eye wall, rain bands, embedded thunderstorms. Computer models grow sophisticated enough to predict tracks, days in advance with reasonable accuracy, but intensity prediction remains elusive. Models struggle to predict rapid intensification, the phenomenon where hurricanes suddenly strengthen much faster than thermodynamic equations suggest possible. The atmosphere contains more complexity than models can capture. Small-scale processes, ocean eddies, upper-level wind patterns, moisture, concentrations can trigger feedbacks that cascade into major changes. Hurricane Patricia, forming off the coast of Mexico in October 2015, demonstrates this unpredictability. Patricia intensifies from Category 2 to Category 5 in 24 hours. Winds accelerate from 110 to 215 miles per hour, an increase unprecedented in the satellite era. The storm's central pressure drops to 872 millibars, breaking the Western Hemisphere record that had stood for decades. Meteorologists scramble to understand the intensification. Patricia formed over unusually warm water, ocean temperatures exceeding 85 degrees Fahrenheit to depths of 300 feet. It encountered zero wind shear, no upper-level winds to disrupt its circulation, and it remained compact, with hurricane-force winds extending only 15 miles from the center, allowing the eye to contract rapidly. But those conditions, while favorable, don't fully explain Patricia's explosive growth. Something about the storm's internal dynamics, something not captured in forecast models, allowed it to achieve intensity levels thought impossible. Patricia weakens rapidly after landfall, sparing Mexico the worst-case scenario. But the storm raises troubling questions. If Patricia could intensify that rapidly in 2015, what intensification rates might become possible as oceans continue warming? What limits exist on hurricane intensity? Do any limits exist? The historical record reveals patterns that weren't obvious when events occurred. Major hurricanes cluster in time. The 1930s and 40s saw numerous intense storms. The 1970s and 80s were quieter. The early 2000s brought another surge of activity. These patterns correlate with ocean temperature cycles, the Atlantic multi-decadal oscillation, a natural variation in North Atlantic temperatures that operates on 60 to 80-year timescales. But something changes in the early 21st century. The oscillations continue, but they superimpose on a rising baseline. Warm periods become warmer. Cool periods don't cool as much as they did historically. The overall trend is unmistakable. Ocean heat content increases decade after decade, and with that increase comes a shift in hurricane behavior. Rapid intensification events become more common. Storms maintain intensity closer to land instead of weakening during approach. Rain rates increase. Hurricanes carry more moisture because warmer air holds more water vapor. The proportion of Category 4 and 5 storms rises relative to weaker systems. Meteorologists recognize they're witnessing a transition, not just more intense hurricanes, but different hurricanes, storms that behave in ways previous generations never encountered. The question becomes, where does this transition lead? By 2024, the pattern has become undeniable. Ocean temperatures in the Gulf of Mexico and Caribbean regularly exceed historical maxima. The warm pool of water above 82 degrees Fahrenheit, the threshold temperature required for hurricane formation, expands poleward, allowing storms to form and intensify in regions previously too cool to support them. The loop current, that river of Caribbean warmth flowing through the Gulf, shows unusual behavior. Instead of remaining at depth, warm water rises toward the surface more frequently. Eddies break off from the main current, creating isolated pools of deep heat scattered across the Gulf. These eddies act as fuel dumps, concentrated sources of energy that hurricanes can rapidly exploit. In August 2024, Hurricane Debby demonstrates the phenomenon. The storm intensifies to Category 4 status, while moving over an eddy northeast of the Yucatan Peninsula. It weakens temporarily after leaving the eddy, then re-intensifies when it encounters another warm pool near Florida's Big Bend. The cycle repeats: intensification over deep warm water, weakening over shallower heat, intensification again over the next eddy. Debby behaves not like a single storm, but like a storm repeatedly reborn, finding new fuel sources that previous hurricane generations rarely encountered. Meteorologists studying satellite data realize the Gulf has become more favorable for hurricane intensification than at any time in the historical record. Not just warmer, but structurally different, with heat distributed in patterns that allow storms to maintain intensity or re-intensify even when conditions should favor weakening. The Gulf transforms from a region where hurricanes sometimes intensify into a region where rapid intensification becomes expected rather than exceptional. Then comes October 9th, 2024. Hurricane Milton forms as a tropical depression in the western Gulf of Mexico. Initial forecasts predict gradual strengthening to Category 2 status before landfall on Florida's west coast. The forecast proves spectacularly wrong. Milton finds conditions that haven't existed in the Gulf since the Younger Dryas period 12,000 years ago, or perhaps even earlier. Water temperatures at depth exceed 90 degrees Fahrenheit. The loop current eddies align perfectly with the storm's track, providing continuous fuel. Wind shear remains nearly zero. Upper-level atmospheric patterns support rather than disrupt the storm's circulation. Every factor that limits hurricane intensity vanishes simultaneously. The storm doesn't gradually intensify. It explodes. In 18 hours, Milton transforms from a minimal hurricane into a Category 5 monster, with winds of 195 miles per hour and central pressure of 877 millibars, shattering Hurricane Patricia's Western Hemisphere record. But the numbers, as extraordinary as they are, tell only part of the story. Milton exhibits behaviors that go beyond mere intensity. The storm develops organizational structures, mesovortices, arranged in geometric patterns, temperature inversions that remain stable for hours, electromagnetic fields strong enough to disrupt GPS satellites. Milton doesn't just break records. It demonstrates atmospheric physics that models don't predict. In the National Hurricane Center's archives, researchers begin pulling historical documents, searching for precedents. They find descriptions in Spanish colonial records of storms that sound eerily similar, hurricanes that intensified with shocking speed, maintained extreme intensity despite unfavorable conditions, produced phenomena that observers struggle to describe. A 1681 account from Cuba mentions a storm that arrived with winds that moved in circles within circles, as though many tempests combined in one. A 1705 report from Jamaica describes a hurricane where the very air did seem to glow with lightning continuous, and the sea appeared to boil though no volcano was near. These historical accounts, previously dismissed as exaggeration or misunderstanding, suddenly seem like accurate observations of storms exhibiting Milton-like behavior. Perhaps Milton isn't unprecedented. Perhaps we've seen this before in eras when instrumental measurements didn't exist, when the only records came from survivors who lacked scientific vocabulary to describe what they witnessed. Perhaps these hypercanes have always occurred occasionally, during specific combinations of ocean conditions and atmospheric patterns. Perhaps they vanish from collective memory because they're rare enough that generations pass between events. Or perhaps something else is happening, something that makes 21st century Miltons different from their historical predecessors. The forge that creates hurricanes operates continuously. Every summer, tropical waves roll off the coast of Africa, riding easterly winds across the Atlantic. Most dissipate harmlessly. A few find conditions favorable for development, warm water, low wind shear, adequate moisture, and organize into tropical storms. Fewer still achieve hurricane status, and a tiny fraction, perhaps 1 or 2 per year, intensify to Category 4 or 5. This forge operated the same way for thousands of years, producing storms within a predictable range of intensities. Yes, occasional outliers like the Great Hurricane of 1780 or Hurricane Camille exceeded normal parameters, but they remained outliers, separated by decades or centuries. Milton suggests the forge has changed. The range of possible intensities has expanded. The mechanisms that previously limited hurricane strength have weakened, or, in some cases, vanished entirely. The atmosphere and ocean have entered a new regime, where storms can achieve states that were previously theoretical. We're not experiencing more hurricanes. Total hurricane counts remain within historical norms, but we're experiencing different hurricanes, storms that tap into energy sources that previous generations of hurricanes couldn't access. The question climatologists now face: is Milton a preview of the new normal, or is Milton itself an outlier, an extreme event even within the new regime? The answer may determine the fate of every coastal city on Earth. 4 billion years ago, the first storms formed on a cooling planet. 12,000 years ago, transition period hypercanes raged during the Younger Dryas. 8,000 years ago, modern hurricanes emerged as climate stabilized. Throughout human history, these storms have shaped civilizations, destroyed fleets, killed hundreds of thousands, but they operated within limits. Even the strongest hurricanes dissipated eventually. Even the most favorable conditions had ceilings. The atmosphere and ocean, for all their power, remained bounded systems with maximum possible intensities. Milton suggests those bounds have shifted, or perhaps the bounds remain where they always were, but we're now approaching them regularly rather than occasionally. Perhaps the gap between ordinary hurricanes and the theoretical maximum intensity is narrowing. Perhaps storms like Milton represent not new physics, but familiar physics operating at scales we haven't seen in human history. Either way, the implications are profound. If the forge of storms has fundamentally changed, then everything we've built along coastlines, everything we've designed based on historical storm records, may be inadequate for what's coming. The monsters aren't waking. They're being forged anew, in a process that follows ancient patterns but produces unprecedented results. Inside Hurricane Milton, air rises at 200 miles per hour. This velocity exceeds the terminal velocity of skydivers, the speed at which falling humans reach equilibrium between gravity and air resistance. Inside Milton's eye wall, water droplets and ice crystals accelerate upward faster than a skydiver falls downward. The updrafts transform the eye wall into a vertical wind tunnel 40,000 feet tall, moving mass at rates that strain the physical limits of what atmospheric pressure gradients can achieve. At the surface, the ocean feeds this engine. Water evaporates from wave crests whipped into spray by 200-mile-per-hour winds. The spray doesn't fall back to the ocean, it's caught immediately by updrafts and lifted into the storm circulation. Each second, Milton's eye wall ingests thousands of tons of water, converting liquid to vapor, then lifting that vapor to altitudes where temperatures plunge below freezing. The energy required to maintain these updrafts should exhaust itself within hours. Storms are heat engines, converting thermal energy from warm oceans into kinetic energy of wind. The second law of thermodynamics dictates that no engine operates at 100% efficiency. Some energy always dissipates as waste, heat, turbulence, or friction. But Milton approaches efficiencies that shouldn't be possible. The storm minimizes energy losses by developing organizational structures that previous hurricanes never achieved. It's not just a storm. It's an optimized storm, as if atmospheric physics has discovered new configurations that maximize power output. The mesovortices appear first on radar, as small-scale rotation signatures embedded within the larger eye wall circulation. This phenomenon occurs occasionally in strong hurricanes, mini-tornadoes spinning within the parent storm. Usually they form randomly, last minutes, then dissipate as the chaotic turbulence of the eye wall tears them apart. Milton's mesovortices don't behave randomly. 6 distinct vortices form in a ring around the central eye, each positioned exactly 60 degrees from its neighbors. Each vortex measures approximately 3 miles in diameter. Each sustains wind speeds exceeding 300 miles per hour, faster than the strongest tornadoes ever recorded, and they maintain these positions for hours, rotating around the eye like planets orbiting a star. The geometric arrangement shouldn't be stable. Turbulence should disrupt the pattern. Mesovortices should merge or dissipate or drift out of position. Atmospheric flows don't naturally organize into perfect hexagonal arrays. Such patterns appear in laboratory experiments under carefully controlled conditions, not in the chaotic violence of Category 5 hurricanes. Yet Milton maintains the pattern. Satellite imagery reveals the mesovortices carving grooves in the ocean surface. Each vortex creates a local low-pressure area that depresses sea level by several feet. As the vortices rotate around the eye, they spiral inward slightly, their grooves forming patterns that look disturbingly artificial from space. Geometric spirals that could be mistaken for designs drawn by intelligent hands rather than atmospheric phenomena. The grooves remain visible for hours after the mesovortices dissipate, slowly filling as ocean waves smooth the surface. Marine researchers studying post-storm imagery note that the grooves extend to depths of 50 feet or more, far deeper than normal wave action penetrates. The mesovortices weren't just spinning air, they were drilling into the ocean itself. But the mesovortices serve a function beyond their immediate destructiveness. Each acts as an auxiliary circulation center, a sub-engine feeding energy into the main storm system. Normally, hurricane eye walls contain a single circulation center, the area of lowest pressure around which winds rotate. Milton develops 7 centers, the main eye plus 6 mesovortex cores. Each mesovortex draws air inward, accelerates it to extreme velocity, and ejects it upward into the eye wall's main updraft. The process resembles a compound engine, where multiple pistons drive a single crankshaft. The configuration allows Milton to process more energy per unit time than a single center storm could manage. The main eye wall's updraft becomes supercharged by contributions from the mesovortices, achieving velocities that single center storms cannot sustain. Aircraft reconnaissance data reveals another peculiarity. The mesovortices oscillate in synchronized rhythm. Their rotation rates vary slightly, speeding and slowing, but the variations follow a pattern. When one mesovortex accelerates, its neighbors decelerate slightly, then reverse the pattern. The oscillations occur at frequencies of approximately once per minute, too slow to be random turbulence, too regular to be coincidental. The mesovortices are coupled. They communicate through pressure waves propagating through the eye wall, maintaining coordination despite being separated by miles of violently turbulent air. This coupling represents a form of self-organization that atmospheric physics doesn't predict. Turbulent flows normally remain chaotic, with no long-range correlations. Yet Milton's mesovortices maintain phase relationships across distances that should prevent any coupling mechanism from operating. How? We don't know. The main eye wall becomes something stranger than a simple ring of intense winds. It develops layered structure, distinct altitude bands with different properties, each band somehow remaining separate from its neighbors, despite no physical barrier between them. Aircraft instruments detect this stratification while flying through the eye wall at various altitudes. At 10,000 feet, temperature and humidity remain relatively constant across the eye wall's width. At 20,000 feet, both variables show rapid variations, patches of warm, dry air adjacent to regions of cold, saturated air, with boundaries between them measuring less than a mile across. These boundaries shouldn't remain sharp. Turbulent mixing should blur them within minutes, equalizing temperature and moisture across the eye wall. Instead, the boundaries persist for hours, as if invisible walls separate different air masses. At 30,000 feet, the structure becomes even more defined. Aircraft encounter temperature inversions, layers where air becomes warmer with increasing altitude, the opposite of normal atmospheric behavior. These inversions span horizontal distances of several miles, but vertical distances of only hundreds of feet. They're thin, stable, and completely unexpected in the violent environment of a hurricane eye wall. The inversions trap air masses, preventing vertical mixing. Warm air overlays cold air, creating stable layers that move upward together while maintaining their separation. It's reminiscent of how liquids of different densities can form distinct layers in a container, except this is happening in gas, at high velocity, under conditions that should make any layering impossible. The stratification serves a purpose. It reduces turbulent energy loss. When air flows smoothly in layers rather than mixing chaotically, less energy dissipates as heat. Milton has somehow stumbled upon or developed a configuration that minimizes one of the fundamental inefficiencies of atmospheric heat engines. Water droplets caught in the updrafts undergo transformations that read like a catalogue of extreme physics. They begin as spray torn from wave crests, droplets measuring millimeters in diameter. The updrafts accelerate them from 0 to 200 miles per hour in seconds. Acceleration forces exceeding 100 Gs, enough to liquefy most solid materials. The droplets should disintegrate under these forces, breaking into smaller droplets or even atomizing into mist. They don't. Surface tension holds them together as they rocket upward, 20,000 feet, 30,000, 40,000. Temperature drops from 90 degrees Fahrenheit to minus 60 degrees. The droplets should freeze solid the moment they reach below freezing altitudes. They don't do that either. Supercooled water can remain liquid below its freezing point if it lacks nucleation sites, impurities, or ice crystals that trigger crystallization. Milton's updrafts are so powerful they carry water to minus 40 degrees Fahrenheit while it remains liquid, a phenomenon normally seen only in carefully controlled laboratory conditions. Then, at some altitude different for each droplet, depending on precise conditions, crystallization occurs. The supercooled water flash freezes, releasing latent heat that warms the surrounding air. This heat release reinforces the updraft, making it stronger, allowing it to carry more water higher, creating a feedback loop. But the ice crystals don't fall. The updrafts continue supporting them, allowing them to accumulate more water vapor, growing larger. Some reach sizes comparable to golf balls, hailstones forming in a tropical hurricane, an environment where hail shouldn't exist. Eventually gravity wins. The hailstones fall, entering warmer air, beginning to melt. But before complete melting occurs, they encounter another updraft and rise again, refreezing in the cold upper levels. Aircraft crews collect hailstones from Milton after they've finally fallen. Laboratory analysis reveals concentric layers, alternating rings of clear and opaque ice, like tree rings. Counting the layers provides a measure of how many times each stone cycled through the eye wall. 15 cycles. Some hailstones underwent 15 freeze-thaw iterations before finally escaping the eye wall and falling to the surface. Each cycle required approximately 10 minutes, meaning these stones remained aloft for more than 2 hours, repeatedly ascending and descending through 40,000 feet of turbulent atmosphere. The energy required to maintain this cycling exceeds what models predict hurricanes can sustain. Each kilogram of water lifted 40,000 feet requires approximately 400 kilojoules of energy. Milton lifts thousands of tons per second. The power output approaches 10 to the 16th watts, 10 million billion watts, a number comparable to total human global energy consumption. From a storm 200 miles across, the hailstones, when they finally fall, descend as supercooled rain droplets that remain partially frozen despite passing through warm air. They strike the ocean surface still containing ice crystals at their cores, creating a sound like billions of tiny bells ringing across thousands of square miles. Sailors who survive in the periphery of the storm report this sound a high-pitched tinkling that carries over the roar of wind, a sound no hurricane has produced before in living memory. Lightning transforms the eye wall into a continuous electrical discharge. 3,000 strikes per minute, 50 per second, a rate that makes individual flashes indistinguishable. The lightning doesn't flash. It glows, creating a flickering illumination that turns night into a strobing approximation of day. The electromagnetic energy release exceeds that of severe thunderstorms by orders of magnitude. But these aren't ordinary lightning strikes. They carry voltages 10 times higher than typical bolts, measuring billions of volts rather than hundreds of millions. The current flowing through each discharge channel approaches 200,000 amperes, enough to vaporize any conductor it contacts. The high voltage stems from the extreme charge separation Milton achieves. Ice crystals in the upper eye wall, 30,000 feet altitude, accumulate positive charge through collision processes. Each collision between ice particles transfers electrons, leaving some particles positively charged and others negatively charged. Updrafts carry positive charges higher, gravity pulls negative charges lower. The separation distance exceeds 10 miles vertically, far greater than in normal thunderstorms. With charges separated by such distances, the voltage required to spark a discharge increases proportionally. When discharge finally occurs, the lightning bolt carries all that accumulated potential energy. Some bolts travel horizontally rather than vertically, connecting different parts of the storm system across distances exceeding 50 miles. These horizontal discharges, called spider lightning, appear on satellite imagery as branching networks stretching across the entire storm field. They're not leaping between cloud and ground. They're connecting different charge centers within the storm's three-dimensional structure. Other bolts shoot upward, out of the storm entirely, reaching into the stratosphere 60 miles above Earth's surface. These upward discharges create sprites, transient, luminous events that last milliseconds, appearing as red or blue columns of glowing plasma. Sprites occur above severe thunderstorms occasionally. Milton produces them continuously. The electromagnetic field generated by this lightning storm becomes detectable from space. Instruments aboard the International Space Station, designed to monitor Earth's magnetic field for research purposes, to register a strong magnetic anomaly centered on Milton's position. The anomaly rotates with the storm, showing field strength variations that match the eyewall's rotation period. Ground-based measurements confirm the field. Magnetometers, hundreds of miles from the storm, detect perturbations in Earth's magnetic field that correlate with Milton's lightning activity. The storm has created a magnetic disturbance comparable to what solar storms produce, except this disturbance originates in Earth's atmosphere rather than from space. The mechanism isn't mysterious. Lightning creates electromagnetic fields, and continuous lightning creates continuous fields. But the magnitude is extraordinary. Creating a magnetic field detectable from space requires sustained current flow measured in millions of amperes. Milton maintains this current for hours, powered by the charge separation created by its updrafts. The field affects technology within 1,000 miles of the storm. Radio communications experience interference. GPS satellites transmit signals that pass through Milton's ionized atmosphere, where free electrons scatter the signals unpredictably. Position calculations that normally achieve accuracy within a few feet suddenly show errors of hundreds of feet. Ships navigating near the storm report compass anomalies, variations of several degrees from true north. The storm's magnetic field, while weak compared to Earth's main field, is strong enough to deflect compass needles when the field lines align favorably. Military aircraft operating in the region switch to inertial navigation systems, gyroscope-based technology that doesn't depend on external signals. These systems, normally used only in electromagnetic warfare environments or near the magnetic poles, become necessary for routine operations near Milton. The storm creates its own electromagnetic environment, a bubble of charged particles and magnetic fields that extends far beyond the visible cloud structure. Below the storm, the ocean reveals its own peculiarities. Sensors dropped by research vessels detect infrasound acoustic waves at frequencies below 20 Hz, beneath the threshold of human hearing. These waves propagate through water at 1,500 meters per second, their wavelengths measuring hundreds of feet. Infrasound travels enormous distances with minimal attenuation. Whale songs, which use infrasound frequencies, can be detected thousands of miles from their source. Milton's infrasound proves even more powerful, reaching hydrophones in the Caribbean, near the Galapagos Islands, eventually detected by monitoring stations near Antarctica, 6,000 miles from the storm's center. The infrasound originates from the interaction between wind and waves. When hurricane winds blow across the ocean surface, they create waves, but not all wave energy propagates horizontally across the surface. Some energy couples into the water column, creating pressure waves that propagate downward and horizontally. Milton's extreme winds generate extreme pressure waves. These waves travel through underwater seamounts, mountain ranges that extend thousands of feet above the ocean floor. The seamounts act as waveguides, channeling acoustic energy along their ridges, allowing it to reach distances where direct propagation would dissipate. Animals respond to the infrasound long before the storm becomes visible. Dolphins evacuate the storm zone 72 hours before Milton forms. Pod movements, tracked by marine biologists, show synchronized migration patterns, groups separated by hundreds of miles all moving north at the same time, despite no visible connection between them. The dolphins detect pressure changes through their auditory systems, which evolved to process underwater sound with extraordinary sensitivity. But the pressure changes, occurring 72 hours before the storm forms, measure fractions of a millibar variations so small that most instruments can't reliably detect them. How do dolphins sense such minute changes? Their inner ears contain structures that respond to pressure variations, but the sensitivity required exceeds what anatomical studies suggest possible. Perhaps they possess additional sensory systems that remain undiscovered organs, or tissues that respond to stimuli we don't yet know how to measure. Sharks exhibit similar behavior, diving to depths exceeding 1,000 feet and remaining there until after the storm passes. At those depths, they're below the influence of surface waves and pressure variations. They remain in the deep scattering layer, the zone populated by squid and deep-sea fish where they normally wouldn't hunt. The evacuation strategy suggests knowledge passed through evolutionary time. Sharks have existed for 400 million years, experiencing countless hurricanes. Those individuals that sensed storms early and dove deep survived. Those that remained near the surface did not. Natural selection operating over geological timescales could encode storm avoidance behavior at instinctual levels. But Milton triggers more extreme responses than ordinary hurricanes. The animals don't just avoid the storm's path, they flee perpendicular to it, as if avoiding not a line of danger but an area of danger much larger than the visible storm. What are they sensing that our instruments miss? Seabirds vanish from coastal areas 3 days before Milton makes landfall. Species that normally feed near shore, pelicans, gulls, terns, disappear entirely, their populations relocating inland or hundreds of miles along the coast. The evacuation occurs despite clear skies and calm seas, no visible indication that a major storm approaches. Birds navigate using multiple sensory systems, visual landmarks, the sun's position, stars, Earth's magnetic field, perhaps even subtle atmospheric cues that science doesn't fully understand. Any of these systems could theoretically detect storm precursors days in advance. But the timing remains remarkable. 3 days before landfall means the birds are responding to conditions present when Milton was barely a tropical depression. A disorganized cluster of thunderstorms that forecasters rated as having only moderate development potential. The birds knew something the forecasters didn't. Migration patterns show additional peculiarities. Instead of moving directly away from the storm's eventual track, birds disperse in multiple directions, some north, some south, some inland, as if avoiding not a point but a zone. The dispersal pattern matches the eventual extent of Milton's influence, the region where the storm's outer rain bands will eventually reach. It's as if the birds can sense the storm's future extent before that extent becomes determined. This seems impossible, yet the correlation between evacuation zones and eventual storm impact areas proves statistically significant across multiple species. Perhaps the birds are responding to atmospheric conditions, subtle changes in pressure, humidity, or electrical potential that will eventually cause the storm to expand to particular dimensions. Perhaps they've evolved to recognize patterns invisible to human instruments. Or perhaps they're sensing something about the storm's development trajectory that our models fail to capture. The evacuation extends beyond marine and aerial species. In Georgia, 500 miles from Milton's center, seismographs detect rhythmic pulses that match the storm's rotation period. Each pulse lasts seconds, repeats every 6 minutes, and propagates through bedrock as pressure waves barely distinguishable from background noise. The pulses aren't earthquakes. Earthquake. Sensors are designed to detect sudden releases of tectonic energy, sharp spikes in ground motion that decay within minutes. Milton's signals are different, sustained, rhythmic, gradually increasing in amplitude as the storm intensifies. They're pressure waves in Earth's crust, caused by the storm's low central pressure literally deforming the planet's surface. Atmospheric pressure normally varies by a few millibars between high and low pressure systems, differences measuring a few tenths of 1% of standard pressure. These variations cause negligible ground deformation, measurable only by extremely sensitive GPS instruments. But Milton's central pressure drops to 877 millibars, more than 100 millibars below standard pressure. This difference, applied across the storm's circulation, creates enough force to lift the ground beneath the eye by 3 inches. GPS stations designed to monitor tectonic motion instruments, capable of measuring position changes at millimeter precision, register this deformation in real time. The ground rises as the storm approaches, peaks when the eye passes overhead, then subsides as the storm moves away. The deformation propagates through bedrock as elastic waves, the same type of waves generated by earthquakes, but with different characteristics. Earthquake waves arrive as sharp pulses. Milton's waves arrive as sustained oscillations, their frequency matching the storm's rotation rate. Seismic monitoring networks issue warnings for earthquake activity that never materializes. The algorithms that detect genuine earthquakes cannot distinguish between tectonic events and atmospheric pressure deformations that happen to propagate through the same medium. Milton has become powerful enough to confuse systems designed to monitor the solid Earth, creating signals that mimic geological processes despite originating in atmospheric phenomena. At 1400 hours on October 9th, Milton's eye passes over Deep Ocean Monitoring Station 41 North. The platform, a steel structure anchored to the seafloor in water 1,200 feet deep, is designed to withstand Category 5 hurricanes. It carries instruments measuring every parameter of ocean state: temperature, salinity, current velocity, wave height, dissolved oxygen, even acoustic properties. The platform survives the passage, barely. Support beams bend, instrument mounts shear. The anemometer, designed to measure winds up to 200 miles per hour, spins so fast its bearings fail and it seizes. But enough sensors continue functioning to capture data during Milton's most intense phase. The data reveals ocean conditions that shouldn't exist. Wave heights reach 82 feet from trough to crest, measurements that strain the instrument's design limits. But it's not the height that proves most remarkable, it's the direction. Ocean waves normally radiate outward from a storm center, propagating in directions determined by wind patterns. Milton's waves converge, moving inward toward the eye. The storm has reversed wave propagation. Under normal conditions, wind stress transfers momentum to the ocean surface, creating waves that travel in the wind's direction. As waves propagate away from the storm, they carry energy outward, helping to dissipate the storm's intensity. This energy transfer represents one of the natural limits on hurricane strength, but Milton's pressure gradient becomes so extreme that pressure forces overwhelm wind stress. Air pressure differences across the storm create forces that pull water toward the low-pressure eye. The ocean surface develops a depression, a pit measuring 12 feet deep and 5 miles across directly beneath the eye. Water flows into this depression from all directions, creating converging wave patterns. The waves don't break normally. Instead of white caps forming when wave height exceeds stability limits, the waves collapse into the central depression, their energy channeled downward rather than dissipated at the surface. This creates a feedback mechanism. Converging waves concentrate energy. Concentrated energy enhances the surface depression. Enhanced depression creates stronger converging flows. The cycle reinforces itself, allowing Milton to maintain intensity levels that wave energy dissipation should prevent. Inside the depression, ocean structure breaks down completely. Thermocline's boundaries separating water masses of different temperatures vanish. Instruments detect uniform temperature from surface to depths exceeding 1,000 feet. The ocean has become vertically mixed, its normal layered structure destroyed by forces that penetrate deeper than storm waves should reach. Halocline's boundaries between regions of different salinity also disappear. Salt water and relatively fresh water, which normally remain separated by density differences, mix thoroughly. The mixing occurs despite the fact that diffusion, the natural process that equalizes concentrations, operates far too slowly to explain the uniformity observed. Something is actively mixing the ocean to depths of 1,000 feet within hours. Normal wave action affects only the upper few hundred feet. Even extreme waves generated by major hurricanes don't penetrate beyond 500 feet depth. but Milton isn't generating normal waves. The converging wave patterns create downward currents, jets of water flowing from surface to depth, driven by the collision of waves approaching from multiple directions. These jets reach speeds exceeding 10 miles per hour, fast enough to transport surface water to the abyss in minutes. Marine biologists later discover evidence of this deep mixing in the most tragic way. Deep-sea fish species adapted to high pressure and zero light. Species that normally never venture above 2,000 feet are found dead on the surface in the storm's wake. There, the swim bladders have ruptured, expanded by decreasing pressure as the downward currents pulled them toward the surface. The fish didn't swim upward. They were transported upward against their will, caught in circulation patterns that reached into the deep ocean and extracted organisms that have existed at depth for millions of years. Milton doesn't just affect the surface ocean. It reorganizes the entire water column, creating three-dimensional circulation patterns that extend from surface to abyssal depths. The storm speaks a language written in isotopes. Water molecules consist of hydrogen and oxygen atoms, but these atoms exist in multiple isotopic forms. Oxygen-16 is the most common oxygen isotope. Oxygen-18 is heavier, rarer, but measurably present in all water. The ratio of these isotopes, written as delta O18, serves as a chemical fingerprint indicating water's origin and history. Ocean water has characteristic delta O18 values that differ from rainwater. Deep ocean water has different values than surface water. Water vapor, evaporated from the ocean at different temperatures, carries different isotopic signatures. Rainwater, collected from Milton's outer bands, shows isotope ratios that reveal the storm's secrets. Some samples contain signatures indicating water originated from depths exceeding 1,000 feet, water that shouldn't contribute to storm formation because it normally remains below the mixed layer, isolated from atmospheric processes. Yet Milton somehow accessed this deep water, evaporated it, and incorporated it into the storm's circulation. Other samples show signatures matching climate projections for the year. 2100 isotope ratios predicted to occur when oceans are significantly warmer than present conditions. These future signatures appear in current samples because Milton created temperature and evaporation conditions that won't become widespread for decades. The storm is sampling both spatial extremes, water from depths normally inaccessible, and temporal extremes, conditions representing future climate states. It's as if Milton serves as a probe, revealing what oceans contain at depth and what they will become at the surface as warming continues. Most remarkably, some samples show isotope ratios matching those found in Greenland ice cores from the Eemian interglacial period 130,000 years ago. The Eemian was Earth's last period of warmth, comparable to or exceeding present trends, a time when global temperatures were 2 degrees Celsius warmer than pre-industrial levels, when seas were 20 feet higher, when hippos lived in Britain. The isotope match suggests that Milton produced atmospheric conditions, evaporation rates, temperature profiles, moisture transport patterns identical to storms occurring during the Eemian. We're not just experiencing unusual weather, we're experiencing paleoclimate conditions, storm regimes from Earth's geological past suddenly appearing in the present. Climate scientists studying this isotope data realize they're witnessing not an anomaly but a phase transition. Climate systems don't change linearly. They exhibit threshold behavior, periods of stability, interrupted by rapid shifts to new states. The transition from Ice Age to interglacial occurred over decades, not millennia, as ice sheets collapsed and ocean circulation reorganized. The end of the Younger Dryas period saw temperature changes of 15 degrees Fahrenheit in less than a decade. These transitions involve crossing tipping points, conditions where positive feedbacks overwhelm negative feedbacks, driving rapid change until a new equilibrium emerges. Milton suggests we're approaching a tipping point in hurricane behavior. The storm didn't gradually intensify beyond historical bounds. It suddenly accessed a new intensity regime, operating under dynamics qualitatively different from previous hurricanes. The mechanisms Milton demonstrated, organized mesovortices, stable temperature inversions, converging wave patterns, deep ocean mixing, represent emergent phenomena. They arise only when specific conditions are met, then operate under principles that make them self-sustaining. This is how phase transitions work. Water remains liquid as temperature drops, showing no dramatic changes, until suddenly at 0 degrees Celsius it transforms to ice. The phase transition isn't gradual. It's abrupt, occurring when molecular motion slows to the point where crystalline structure becomes stable. Hurricanes may undergo analogous transitions. Below certain ocean temperature thresholds, they operate as conventional storms, their intensity limited by natural dissipation mechanisms. Above those thresholds, new organizational modes become possible, allowing storms to achieve intensities and behaviors previously impossible. We may have just crossed that threshold. Or perhaps the threshold isn't fixed. Perhaps it varies with other conditions like atmospheric structure or ocean depth distribution. Perhaps Milton crossed a threshold that exists only in specific regions or during specific months. Perhaps what happened in the Gulf of Mexico in October 2024 won't happen elsewhere or at other times. But perhaps it will. Perhaps thresholds are being crossed globally in ways we haven't yet recognized because we're still looking for gradual change rather than sudden transformation. The architecture of chaos, as it turns out, isn't chaotic at all. Milton exhibits organization at every scale, from the geometric arrangement of mesovortices to the layered structure of the eye wall to the three-dimensional ocean circulation extending to abyssal depths. The storm isn't a random collection of winds and clouds. It's a structured system with internal coordination, feedback mechanisms, and emergent properties. Calling it chaos is convenient but incorrect. Chaos implies randomness, unpredictability, absence of pattern. Milton displays none of these characteristics. Its behavior follows principles we don't fully understand yet, but principles nonetheless. The question becomes, is this organization unique to Milton, or is it a general property of hypercanes that we're observing for the first time? If unique, then Milton represents a fluke, extraordinary conditions conspiring to produce extraordinary results that won't be repeated. If general, then every future storm reaching similar intensity will exhibit similar organization. The mechanisms aren't unique to this storm. They're features of atmospheric physics that manifest when energy levels exceed certain thresholds. The data suggests the latter. Milton's organizational features appear too systematically, too reproducibly across the storm's lifespan to be random fluctuations. They represent stable configurations, solutions to atmospheric fluid dynamics that become accessible at high energy densities. We've discovered new physics. Not physics that violates known laws, but physics that operates in regimes we've never observed before. Milton gave us a glimpse into what happens when hurricanes evolve beyond the bounds of historical experience. The architecture of what we called chaos is actually the architecture of order emerging at intensity levels we're only now beginning to reach. The ice remembers everything. In central Greenland, 3 miles beneath the summit of the ice sheet, cylinders of frozen time lie in climate-controlled storage. Each cylinder contains ice that fell as snow thousands of years ago, precipitation that captured chemical signatures of the atmosphere in which it formed. The ice preserves these signatures perfectly, creating an archive that extends back 130,000 years. Scientists analyzing ice cores from the Eemian interglacial period roughly 125,000 years ago find layers that tell a story about storms. The isotope ratios in these layers indicate evaporation occurred from unusually warm ocean surfaces under conditions of extreme atmospheric instability. The deuterium excess, a measure of humidity conditions during evaporation, suggests storm systems transported moisture from tropics to Greenland at rates far exceeding modern hurricanes. The Eemian was Earth's last period of sustained warmth, comparable to what we're creating now. Global temperatures during the Eemian peaked at approximately 2 degrees Celsius above pre-industrial levels, similar to what we expect to reach by mid-century if current trends continue. Sea levels stood 20 to 30 feet higher than today as portions of the Greenland and Antarctic ice sheets melted, and the storms. The storms were different. Ice core chemistry indicates the Eemian experienced rapid intensification events similar to what Milton demonstrated. The storm signatures appear suddenly in the ice record. Single precipitation events that deposited isotope ratios indicating sea surface temperatures and evaporation rates far exceeding anything in the modern instrumental record. Then these signatures vanish for decades or centuries before appearing again. The pattern suggests Eemian hypercanes occurred episodically rather than continuously. They weren't the new normal, they were extreme events within an already warm climate, but they occurred frequently enough to leave multiple signatures in ice spanning thousands of years. Milton's rainwater, analyzed in laboratories days after the storm, shows isotope ratios matching those Eemian signatures, not approximately matching, exactly matching within measurement uncertainty. We're recreating paleoclimate conditions. The storms of 125,000 years ago are returning. The ocean keeps its own records, written in mud. Deep-sea sediment cores from the Gulf of Mexico contain layers that serve as geological storm calendars. When major hurricanes pass over deep ocean, they stir up bottom sediments, clays, and silts that normally remain undisturbed. These sediments get transported by storm-enhanced currents and deposited in patterns that betray their origin. Marine geologists examining sediment cores find storm layers extending back 12,000 years, covering the entire period since the end of the last ice age. The layers appear irregularly, separated by years or decades of normal sedimentation. Each layer represents a single major storm event, its thickness and composition providing information about storm intensity. The record shows something troubling. Storm layers from the early Holocene, 8 to 10,000 years ago, when climate was warming rapidly as ice sheets retreated, are consistently thicker than layers from recent millennia. The ancient storm layers contain coarser sediments transported from greater depths, indicating stronger bottom currents and by extension more intense storms. These paleotempests occurred during the last period of rapid climate warming. As Earth transitioned from ice age to interglacial, the climate system oscillated through multiple states before stabilizing. During these oscillations, hurricanes achieved intensities that modern climate until recently never experienced. The sediment record suggests we're entering a new period of oscillation. The past 50 years show increasing numbers of thick storm layers, their characteristics approaching those found during the early Holocene transition. Milton will leave its own layer 1 of the thickest in the entire 12,000-year record. Future geologists examining cores from the Gulf of Mexico will find sediment containing isotope signatures, chemical traces, and sediment distributions that mark October 2024 as a pivotal moment when storms crossed into a new intensity regime. The loop current holds secrets about what made Milton possible. This current, a river of Caribbean warmth flowing through the Gulf of Mexico, has existed in recognizable form for millions of years. It flows north through the Yucatan Channel, curves east, then exits through the Florida Straits to become part of the Gulf Stream. The current transports warm water at velocities exceeding 3 miles per hour, moving approximately 30 million cubic meters of water per second. But the loop current exhibits variability on multiple timescales. Sometimes it extends far north into the Gulf, reaching toward Louisiana. Other times it retracts south, barely entering past the Yucatan Peninsula. These variations occur over months or years, driven by factors that oceanographers don't fully understand. In October 2024, the loop current extended to its maximum northern position. More significantly, it had shed multiple warm core rings, eddies of concentrated heat that broke off from the main current and drifted westward into the Gulf. These eddies measure 50 to 100 miles across. They contain water with temperatures exceeding 85 degrees Fahrenheit, extending to depths of 3,000 feet or more. While the surface temperature might be only a few degrees warmer than surrounding water, the heat content, the total thermal energy stored in the water column, vastly exceeds normal conditions. Milton tracked directly over 3 of these eddies in succession. Each eddy provided fuel for rapid intensification. As the storm moved from one eddy to the next, it maintained access to deep, warm water that would normally be available only over much larger ocean areas. The eddies acted like refueling stations, allowing Milton to sustain maximum intensity far longer than typical storms. But here's what concerns oceanographers. The loop current is producing warm core rings with increasing frequency. Analysis of satellite altimetry data, measurements of sea surface height that reveal ocean circulation patterns, shows ring formation. Accelerating over the past 2 decades, the increase correlates with rising ocean temperatures. As the Caribbean warms, the temperature contrast between the loop current and surrounding waters intensifies. This enhanced contrast makes the current more unstable, causing it to meander more dramatically and shed rings more frequently. More rings mean more fuel for rapid intensification. More fuel means more Miltons. Deep ocean sensors scattered across the Gulf of Mexico detected Milton's approach long before surface observations revealed anything unusual. These sensors, anchored to the seafloor at depths exceeding 6,000 feet, measure temperature, salinity, and current velocity at multiple depths. Days before Milton formed, the sensors detected pulses of warm water rising from the loop current. The pulses moved upward at velocities measuring several meters per hour, far faster than normal oceanic upwelling. They carried heat from depths of 2,000 feet toward the surface, priming the upper ocean for storm intensification. The mechanism driving these pulses remains unclear. They might be internal waves, oscillations within the ocean that transport energy without surface expression. They might be instabilities in the current structure, fluctuations that cause temporary upward surges, or they might represent responses to atmospheric precursors, subtle pressure changes days before the storm forms that somehow trigger oceanic responses. Regardless of mechanism, the pulses created conditions necessary for Milton's explosive development. They brought deep heat to shallow depths where atmospheric processes could access it. Without these pulses, Milton would have encountered normal ocean stratification, warm surface water underlain by cooler deep water, and likely would have intensified more gradually. The sensors reveal that these pulses occur frequently, not just before Milton but throughout the hurricane season. Most pulses don't lead to rapid intensification because other atmospheric conditions remain unfavorable. Wind shear disrupts storm formation, or dry air inhibits convection, or upper-level patterns steer disturbances away from the warm water. But occasionally, all factors align. Atmospheric conditions become favorable at the exact time and place where oceanic pulses have delivered deep heat to accessible depths. When this alignment occurs, rapid intensification becomes not just possible but likely. We're beginning to understand that hurricane intensification isn't determined solely by sea surface temperature, the metric forecasters traditionally monitor. What matters is the depth distribution of heat, the presence of warm core eddies, and the timing of oceanic pulses that bring that heat within reach of atmospheric processes. Milton demonstrated this principle with devastating clarity. The storm's electromagnetic signature traveled far beyond its visible cloud structure. Radio telescopes in Puerto Rico, designed to study astronomical phenomena, detected unusual signals during Milton's peak intensity. The signals appeared at frequencies between 10 and 100 MHz, characteristic of electromagnetic radiation generated by electrical discharges. But the signal strength exceeded anything previously associated with terrestrial storms. The radiation was powerful enough to be detected from hundreds of miles away, creating interference patterns across the electromagnetic spectrum. Analysis of the signals revealed structure. They weren't random noise, but organized pulses occurring at regular intervals matching Milton's rotation period. Each pulse coincided with a lightning cluster in the eye wall, suggesting the storm's continuous lightning created a coherent electromagnetic source rather than random discharges. This coherence has implications. Coherent electromagnetic sources can propagate energy more efficiently than incoherent sources. They can create standing wave patterns, interference effects, and resonances that amplify their effects far beyond what raw power would suggest. Milton's electromagnetic signature reached the ionosphere, the electrically charged layer of atmosphere beginning at 50 miles altitude. Ionospheric monitoring stations detected disturbances in electron density that propagated outward from the storm at the speed of light. These disturbances affected radio propagation across the Caribbean and southeastern United States, creating communication disruptions far from the storm's center. The disturbances also affected GPS satellite signals. The ionosphere normally delays GPS signals in predictable ways that receivers correct automatically. But Milton's electromagnetic effects created ionospheric irregularities that varied too rapidly for standard corrections to compensate. Position errors of several hundred feet appeared across a region spanning 1,000 miles. For most applications, personal navigation, civilian aviation, these errors were tolerable. But for applications requiring precise positioning, surveying, precision agriculture, autonomous vehicles, the errors exceeded acceptable limits. Systems that depend on GPS became temporarily unreliable across a significant portion of the Gulf Coast region. We learned that hypercanes don't just affect weather, they affect the entire electromagnetic environment, creating disturbances that propagate through multiple layers of atmosphere and impact technologies we've come to depend on. Seismic networks across the southeastern United States recorded Milton's passage not as a weather event, but as a geological phenomenon. The storm's low pressure deformed Earth's crust, creating measurable uplift beneath the eye. But the deformation didn't remain confined to the area directly under the storm. Elastic waves propagated through bedrock, traveling hundreds of miles before dissipating. These waves, measuring amplitudes of micrometers, would normally be undetectable, but modern seismic instruments achieve sensitivity sufficient to measure ground motion at nanometer scales. To these instruments, Milton appeared as a sustained source of seismic energy, generating signals for 18 hours continuously. The signals exhibited characteristics unlike any natural seismicity. Earthquake waves arrive as discrete pulses, sharp onsets followed by exponential decay. Volcanic tremor appears as sustained oscillations, but at frequencies determined by magma movement. Tectonic events produce specific wave patterns that seismologists recognize instantly. Milton's signals matched none of these patterns. They were sustained, like tremor, but at frequencies matching the storm's rotation rather than geological processes. They propagated as surface waves, seismic energy traveling along Earth's crust, rather than through its interior, but with amplitudes far exceeding what surface processes normally generate. Seismologists studying these signals realized they were observing atmosphere-solid Earth, coupling at unprecedented scales. The storm wasn't just affecting the ocean beneath it, it was affecting the entire crust beneath the Gulf of Mexico, creating deformations that propagated as elastic waves through geological structures. Some of these waves propagated into the New Madrid seismic zone, a region of central United States known for large earthquakes in the early 19th century. The zone remains seismically active, experiencing dozens of small earthquakes yearly. Concern exists that sufficient stress could trigger larger events. Milton's seismic signature passed through the New Madrid zone, creating temporary stress perturbations of several kilopascals comparable to stress changes produced by distant large earthquakes. These perturbations likely affected when and where small earthquakes occurred, though not their total number or maximum magnitude. But the event raised a troubling question. What happens when multiple hypercanes occur simultaneously? Could their combined seismic signatures create stress perturbations large enough to influence earthquake timing in vulnerable regions? Could atmosphere and solid Earth become coupled in ways that create hazards beyond the storms themselves? We don't know, but Milton demonstrated that the coupling exists and that its effects propagate far beyond the storm's immediate location. Birds provided the earliest warnings that instruments and forecasts missed. Migration patterns tracked by radar ornithology networks showed massive disruptions beginning 3 days before Milton formed. Species following established migratory routes suddenly deviated, moving perpendicular to their normal tracks. Flocks that should have been over the Gulf of Mexico appeared hundreds of miles inland. Birds that normally migrate in October delayed their departures or accelerated their flights to pass through the region before the storm arrived. The deviations affected millions of individuals across dozens of species. The coordination suggests they were responding to common stimuli, not individual decisions by separate flocks, but a collective response to atmospheric conditions that signaled danger. What conditions were they detecting? Pressure changes measured in fractions of a millibar, humidity variations of a few percent, subtle shifts in wind patterns at altitudes where birds fly, perhaps electromagnetic field variations that biological sensors can detect but instruments overlook. Birds evolved over hundreds of millions of years in an atmosphere that regularly produced severe storms. Those individuals that detected storms earliest and modified behavior accordingly survived more often than those that didn't. Natural selection operating over geological time created biological sensor systems optimized for storm detection. These systems apparently detect storm precursors that appear days before meteorological models predict development. The birds weren't responding to an existing storm, they were responding to atmospheric conditions that would become a storm, recognizing patterns that our physics-based models don't yet incorporate. After Milton passed, researchers analyzed atmospheric data from the 3 days before formation, searching for signals the birds might have detected. They found subtle patterns, pressure fluctuations at high altitudes, electromagnetic field variations, infrasound from ocean waves that were themselves responding to approaching atmospheric disturbances. Each signal individually was too weak to be significant, but collectively they created a pattern, a signature of atmospheric instability that biological systems evolved to recognize. We've spent decades developing sophisticated instruments and computer models for storm prediction, yet evolution developed biological sensors that detect formation days before our best technology recognizes danger. Perhaps instead of dismissing animal behavior as instinct, we should study what they're sensing and develop instruments that measure the same phenomena. Milton taught us that nature has sensors we've overlooked and signals we've ignored. Dolphins fled the storm zone 72 hours before satellites showed any organized circulation. Marine mammal tracking data revealed pods moving north in synchronized groups, despite being separated by distances exceeding 100 miles. The synchronization proves remarkable. Dolphins communicate through vocalizations audible across miles, but these pods weren't close enough for acoustic contact. Yet they moved simultaneously, suggesting response to common stimuli rather than communication between groups. Dolphins possess biosonar systems, echolocation capabilities that allow them to sense their environment through sound. But these systems operate at frequencies far above infrasound, detecting objects and prey rather than atmospheric conditions. They also possess lateral line, organs pressure sensors distributed along their bodies that detect minute pressure variations in water. These organs, homologous to similar structures in fish, allow dolphins to sense currents, waves, and pressure gradients with extraordinary sensitivity. Perhaps these organs detect oceanic precursors to storm formation. Days before Milton formed, the loop current eddies were shifting position, sending pressure pulses through the water column. Ocean surface gravity waves generated by atmospheric disturbances, too weak to be classified as storms, were propagating through the region. Deep ocean currents were adjusting to temperature changes. Each of these oceanic changes creates pressure signatures that lateral line organs could theoretically detect. If dolphins learned through experience that specific pressure patterns precede storms, they might evacuate when detecting those patterns, regardless of current weather conditions. But this explanation requires dolphins to possess not just sensors, but prediction, the ability to associate current conditions with future events separated by days. That requires memory, pattern recognition, and some form of anticipatory cognition. We know dolphins are highly intelligent, but recognizing that specific ocean conditions predict storms days in advance requires intelligence of a different order, the ability to correlate phenomena separated in time, to remember patterns from previous storms, to make decisions based on anticipated futures rather than immediate conditions. Milton forced us to reconsider what marine mammals know about their environment and how much longer-term planning their behaviors might involve. Sharks dove deep and remained there for 5 days, 2 days before Milton formed and 3 days after it passed. Species that normally hunt in surface waters descended to depths exceeding 1,000 feet, entering the mesopelagic zone, where light doesn't penetrate and temperatures drop toward freezing. They remained at these depths despite the absence of their normal prey, effectively fasting while waiting for the storm to pass and conditions to normalize. The behavior represents significant cost. Deep dives require energy expenditure as sharks swim against buoyancy. The cold temperatures slow their metabolism but also reduce their ability to process what little food they find at depth. Yet, they undertake this costly behavior routinely before major storms, suggesting the cost of remaining shallow exceeds the cost of diving. What danger do they avoid by diving? Surface waters during hurricanes become violently mixed, with currents changing direction unpredictably and waves creating zones of air-water mixture that provide no support for swimming. Sharks caught in storm conditions might exhaust themselves fighting currents or become injured by collision with debris. But sharks began diving before any surface expression of the storm existed. They were avoiding danger that hadn't yet materialized, responding to precursors that scientific instruments barely detected. Tagging data from multiple species shows the diving behavior correlates with specific barometric pressure thresholds. When pressure drops below approximately 1010 millibars at the ocean surface, still within the range of normal weather systems, sharks begin descending. They remain at depth until pressure rises above that threshold for at least 48 consecutive hours. The 1010 millibar threshold is significant. It represents conditions where storm development becomes increasingly likely, though not certain. Modern meteorology might classify such conditions as favorable for development, but wouldn't issue storm warnings based solely on pressure readings. Yet sharks have evolved to treat this threshold as a dive trigger. Over millions of years of evolution, individuals that dove when pressure dropped below this level survived storms more often than those that used different thresholds or didn't dive at all. Milton demonstrated that this evolved threshold works. Sharks that followed it avoided the storm entirely. Marine researchers monitoring tagged individuals found 0 storm-related mortality among sharks that dove on schedule. In contrast, several individuals that didn't follow typical diving behavior, juveniles, perhaps, that hadn't yet learned the pattern, vanished from the tagged population, presumably killed by storm conditions. Evolution created a prediction algorithm encoded in instinct. That algorithm outperforms our meteorological models at the timescales relevant to individual survival. The chemical signatures in Milton's rainwater tell stories about the future. Isotope ratios, specifically oxygen 18 to oxygen 16, depend on several factors: the temperature of seawater at evaporation, the temperature of the atmosphere through which vapor rises, and the conditions under which precipitation forms. These factors create unique fingerprints that reveal where and how water cycled through the storm system. Laboratory analysis of rainwater collected from Milton's outer bands revealed isotope ratios that climate models predict won't become widespread until late in the 21st century. The ratios indicate evaporation occurred from seawater at temperatures of 93 degrees Fahrenheit, warmer than current Gulf of Mexico surface temperatures, but consistent with projections for the year 2080 under high-emission scenarios. Milton created local conditions temporarily, in specific locations, matching climate states decades in our future. The storm served as a time machine, bringing future ocean-atmosphere interactions into the present for brief periods. Other samples showed different signatures, ratios matching predictions for the year 2100, when models suggest Gulf surface temperatures could regularly exceed 95 degrees Fahrenheit. These samples originated from the storm's core, where the most intense evaporation occurred. The progression of isotope ratios from storm periphery to core creates a timeline: outer bands showing present conditions, intermediate regions showing mid-century projections, the core showing end-of-century forecasts. Each zone of the storm represented a different point in our climate future, all existing simultaneously in three-dimensional space. But perhaps most striking were samples showing isotope ratios matching Eemian ice core signatures. These ratios indicate evaporation conditions that existed during Earth's last sustained warm period, 125,000 years ago. Conditions we're recreating but haven't yet matched globally. The message is clear. Milton operated under thermodynamic conditions, spanning present, near future, distant future, and paleoclimate past. It sampled across the full range of warm Earth ocean atmosphere states, demonstrating that all these states can exist within the structure of a single storm system. We're not gradually approaching future climate conditions. We're experiencing them now, concentrated in extreme events that compress decades or centuries of warming into days or hours of storm activity. The carbon isotopes tell another story, one about how storms and climate interact on longer timescales. Carbon-14, a radioactive isotope created by cosmic rays in the upper atmosphere, exists in all organic matter at concentrations determined by atmospheric carbon dioxide levels during organism growth. Ocean organisms incorporate carbon from dissolved CO2, creating records of atmospheric composition. Plankton killed by Milton's passage and later recovered from surface waters showed carbon-14 ratios, indicating they had been living at depths exceeding 3,000 feet in waters that last contacted the atmosphere decades ago. Milton's deep circulation brought these organisms from the abyss to the surface, creating a mixture of biological components spanning decades of oceanic time. The mixing suggests storms like Milton affect not just immediate weather, but long-term ocean circulation. Deep water brought to the surface must be replaced by surface water descending to depth, a process that affects how oceans store heat and carbon dioxide. Normally, this vertical exchange occurs through slow diffusion, and the global thermohaline circulation, the centuries-long conveyor belt of ocean currents that transports water between surface and deep ocean. Milton accelerated the process dramatically, creating localized upwelling and downwelling that exchanged surface and deep water in hours rather than centuries. If hypercanes become frequent, this accelerated exchange could affect global climate by altering how efficiently oceans absorb atmospheric heat and carbon dioxide. More exchange could potentially increase absorption, temporarily slowing atmospheric warming, or it could bring carbon-rich deep water to the surface where CO2 outgasses, accelerating atmospheric increases. The direction and magnitude of these effects remain uncertain, but Milton demonstrated that storms can affect not just immediate weather, but the long-term processes that regulate planetary climate. We're learning that hurricanes aren't just responses to climate change, they're active participants in Earth's climate system, capable of influencing the very conditions that create them. Milton's legacy extends beyond the immediate devastation. The storm cooled sea surface temperatures by 9 degrees Fahrenheit across a swath 200 miles wide, creating a cold wake that persisted for weeks. This cooling suppressed subsequent storm development, reducing hurricane activity in the Gulf for the remainder of the 2024 season. The cold wake represents negative feedback. Storms limit their own development by consuming the energy that fuels them. This feedback has always existed, preventing hurricanes from maintaining peak intensity indefinitely and providing natural breaks between successive storms. But oceanographers studying post-Milton conditions discovered something troubling. The cold wake wasn't truly cold, it extended only to depths of about 200 feet. Below that level, warm water remained, isolated from the surface by a sharp thermocline that formed after the storm passed. Normally, thermoclines break down over weeks as wind mixing and solar heating gradually restore vertical uniformity. But the post-Milton thermocline proved unusually stable, maintained by salinity differences that Milton created through its intense rainfall. The fresh rainwater, less dense than salt water, formed a cap that prevented deeper warm water from rising. This created a two-layer ocean: cool, fresh surface water, overlying warm, salty, deep water, separated by a density barrier that normal mixing processes couldn't easily overcome. The configuration has implications. The next storm crossing this region would encounter cool surface temperatures that suggest unfavorable conditions. But a storm intense enough to disrupt the thermocline, perhaps through its own deep mixing, would suddenly access the warm water trapped below, potentially triggering rapid intensification. Despite initially encountering what appeared to be storm-suppressing conditions, Milton created conditions that make future rapid intensification more likely, not less. The storm's legacy isn't cooling that prevents subsequent development, but a hidden reservoir of heat waiting for the next sufficiently intense system to unlock it. We're learning that storms don't just respond to ocean conditions, they modify those conditions in ways that affect subsequent storms. The ocean and atmosphere are communicating through hurricanes, exchanging energy and reorganizing structure in feedback loops we're only beginning to understand. The message from tomorrow is clear. What we experienced with Milton isn't future weather brought into the present. It's present weather becoming what the future will hold. The storm operated under conditions that exist now, but will become increasingly common as oceans continue warming. The deep, warm eddies Milton exploited aren't anomalies, they're forming with increasing frequency. The atmospheric patterns that allowed Milton to organize so efficiently aren't departures from normal, they're becoming the new normal. We're not witnessing climate change in the abstract. We're witnessing it in the form of storms that compress decades of warming into days of intensification, that bring paleoclimate conditions back to life, that demonstrate what Earth's atmosphere can do when given access to energy levels that were once rare. Milton spoke in the language of isotopes, seismic waves, electromagnetic fields, and biological responses. The message, decoded, says, "This is what your future looks like. These are the storms your children will consider normal. This is the atmosphere you're creating." The question is whether we're listening. 2.8 million people. That's the number who fled Florida's Gulf Coast in 72 hours, the largest hurricane evacuation in human history. Not the largest natural disaster evacuation, that distinction belongs to events like the 2005 Pakistan earthquake or Typhoon Haiyan in the Philippines, but the largest evacuation specifically for a hurricane, exceeding even the mass departures before Hurricane Irma in 2017. The evacuation began officially at 1400 hours on October 6th, when the National Hurricane Center upgraded Milton to a hurricane and forecast models showed it tracking toward Tampa Bay. But many residents didn't wait for official orders. Traffic cameras on Interstate 75, the primary evacuation route running north from southwestern Florida, showed congestion beginning the previous evening, as people who remembered previous storms or who monitored atmospheric conditions themselves decided not to wait. By dawn on October 7th, all northbound lanes carried bumper-to-bumper traffic. By noon, the congestion extended 200 miles from Fort Myers to beyond Ocala. Travel times that normally required 3 hours stretched to 12. Gas stations ran dry. Rest areas filled beyond capacity. The exodus created its own logistical crisis even before the storm made landfall. But everyone moved in the same direction. Away from the coast, away from the storm surge zones, away from the barrier islands that would become temporarily uninhabitable. Emergency manager Rebecca Torres coordinated the evacuation from Hillsborough County's Emergency Operations Center, a bunker-like facility designed to remain functional through Category 5 impacts. She'd managed evacuations before. Hurricane Irma in 2017 required moving 800,000 people from the Tampa Bay region. That evacuation, despite its challenges, proceeded relatively smoothly because the storm's track remained uncertain until 48 hours before landfall. Milton was different. The forecast track showed remarkable consistency from the moment the storm became a named system. Computer models agreed a rare consensus that removed the usual uncertainty about where the storm would strike. Milton would hit Tampa Bay. The only questions were when and how strong. The certainty helped in some ways. Residents in the direct path knew they needed to evacuate. Counties south and north of the projected track could focus resources on sheltering rather than evacuation. Emergency managers could pre-position supplies and personnel with confidence they'd be where needed. But certainty also created problems. Everyone in the evacuation zones left simultaneously. No one waited to see if the forecast would change. No one hoped the storm might turn away. The roads couldn't handle the sudden demand. Torres activated the contraflow plan, reversing inbound lanes on Interstate 75 to create additional northbound capacity. Police blocked entrance ramps from local roads, reserving the interstate exclusively for evacuation traffic. The measure doubled roadway capacity but created new problems. Cities along the route couldn't access the interstate to send supplies or emergency vehicles south. The evacuation became a one-way valve. Traffic could flow north, but nothing could flow south. The Gulf Coast region would be cut off from external assistance until after the storm passed and contraflow ended. The Kennedy Space Center executed Protocol 7 maximum protection procedures used only for the most extreme threats. Protocol 7 had been activated 3 times previously, once for Hurricane Charlie in 2004, once for Hurricane Matthew in 2016, once for Hurricane Dorian in 2019. Each time, the protocol proved successful. Facilities survived without critical damage. But Milton represented conditions beyond what previous Protocol 7 activations had faced. The storm would pass within 100 miles of the Space Center, with winds potentially exceeding 180 miles per hour. Storm surge could reach 20 feet despite the facility's location on the Atlantic side of the peninsula, where surge predictions were lower than on the Gulf side. The protocol required moving spacecraft and sensitive equipment from the vehicle assembly building and other exposed structures into reinforced bunkers originally designed during the Cold War to protect against nuclear attack. These bunkers, built into the ground with concrete walls 6 feet thick, could withstand wind-driven missiles, flying debris, even partial structural collapse of buildings above them. Engineers work 24 hours a day moving hardware. The Artemis program's Orion spacecraft, valued at over $1 billion, was disconnected from test equipment, placed in protective containers, and rolled into Bunker 3. Satellite components awaiting launch were similarly secured. Computer systems containing irreplaceable data were backed up, and the backups distributed across multiple locations. The vehicle assembly building, itself one of the largest buildings by volume in the world, couldn't be protected. Its doors, each tall enough to admit assembled Saturn V rockets, couldn't be strengthened beyond their existing design limits. If Milton's winds exceeded 190 miles per hour, those doors would fail. The building interior would pressurize, potentially causing catastrophic structural failure. Engineers calculated the building could withstand 180 miles per hour with 90% confidence. Milton's predicted winds at the Space Center, 170 to 190 miles per hour. They were within the margin of survival barely. Disney World closed for the 5th time in its history. The previous closures had been for Hurricane Floyd in 1999, Hurricane Francis in 2004, Hurricane Matthew in 2016, and Hurricane Irma in 2017. Each closure cost the company tens of millions of dollars in lost revenue, but safety concerns overrode economic considerations. The decision to close came 72 hours before Milton's projected landfall, earlier than any previous closure. 65,000 tourists were staying in Disney properties when the announcement came. Most had arrived expecting a normal vacation. Now they faced evacuation from a region about to experience a catastrophic hurricane. Disney activated emergency protocols developed over decades of operating in Florida's hurricane zone. Hotel guests received instructions on evacuation routes and schedules. The company chartered buses to transport those without vehicles. Orlando International Airport added flights and extended hours to handle the surge of departing tourists, but the airport couldn't accommodate everyone. By October 7th, all commercial flights out of Orlando were fully booked for 3 days. Rental cars became unavailable. Some tourists, particularly international visitors who couldn't easily return home on short notice, chose to shelter in place at Disney hotels rather than attempt evacuation. Disney's hotels, built to modern hurricane standards, could provide relative safety. But relative remained the operative word. The buildings could withstand Category 3 winds. Milton was forecast to make landfall as Category 5, and might still be Category 4 when it reached Orlando, 75 miles inland. Park employees, over 70,000 people who kept Disney World operating, faced their own evacuation decisions. Many lived in mobile homes, structures that become death traps in major hurricanes. The company opened several hotels to employees, providing free shelter to those who couldn't evacuate but lived in vulnerable housing. The parks themselves, Magic Kingdom, Epcot, Hollywood Studios, Animal Kingdom, were secured as much as possible. Outdoor equipment was moved indoors or tied down. Windows were shuttered. Backup generators were fueled and tested. The parks would survive, probably. But decorations, signs, landscaping, all the details that created Disney's famous atmosphere were exposed to winds that could turn them into dangerous projectiles. Marcus Webb, a petroleum engineer for Chevron, coordinated the shutdown of 27 oil platforms in the Gulf of Mexico. Each platform required specific procedures, securing wellheads, depressurizing systems, evacuating personnel, ensuring automated systems could safely manage the platform's status during the storm. Under normal circumstances, shutting down a single platform required 8 to 12 hours. Webb had 72 hours to shut down 27. The platforms operated continuously, extracting oil and natural gas that flowed through pipelines to shore-based refineries. Shutting them down meant stopping production worth millions of dollars per day. But the alternative, risking catastrophic spills if storm damage breached containment systems, was unacceptable both economically and environmentally. Webb prioritized based on platform location and storm track. Platforms in Milton's direct path received attention first. Those on the periphery could wait. Helicopters transported shutdown crews from platform to platform in a carefully choreographed sequence. The procedures were well practiced. Gulf operators shut down platforms before every major hurricane. The process had become routine, an expensive routine, but one that prevented disasters like the Deepwater Horizon spill that occurred when a different kind of failure overwhelmed safety systems. But Milton created complications. The storm's rapid intensification compressed timelines. Platforms that weren't initially in the forecast path suddenly faced direct impact as Milton's track became better defined. Wave heights increased faster than weather models predicted, making helicopter operations dangerous and eventually impossible. Webb made the decision to leave several platforms only partially secured. Personnel had been evacuated that was non-negotiable. But some final shutdown procedures remained incomplete when wave heights exceeded 50 feet and further helicopter flights became impossible. Those platforms would have to weather the storm with systems in unknown states, some equipment secured, some still operating, automated systems making decisions in circumstances beyond their programming parameters. Webb and his team could only monitor remotely and hope the platform's structural integrity would hold. If it didn't, oil would spill into the Gulf, adding environmental disaster to meteorological catastrophe. Dr. James Harrison faced a different kind of evacuation challenge, moving 3,000 zoo animals. As Director of Veterinary Services for Zoo Tampa, Harrison coordinated the most complex logistical operation in the zoo's history. Large animals, elephants, rhinos, hippos, giraffes, couldn't be evacuated. Their transport required specialized equipment and preparation time the emergency didn't allow. These animals would shelter in reinforced facilities designed to withstand Category 5 winds. But smaller animals, primates, big cats, birds, reptiles, could be evacuated, and the zoo's disaster plan called for moving them to facilities inland. Partner zoos in Georgia and Alabama had agreed to provide temporary housing. The challenge was transport. Commercial carriers wouldn't accept wild animals on short notice. The zoo's own trucks were insufficient for 3,000 animals. Harrison requisitioned school buses, delivery vans, even personal vehicles from staff members. Each vehicle required modification cages secured, ventilation ensured, temperature control maintained. The animals themselves presented challenges. Many were dangerous. All were stressed by the disruption of routine. Sedation helped, but carried risks if dosing was incorrect or animals reacted unpredictably. They could die during transport. Harrison prioritized endangered species first. A breeding pair of Florida panthers, part of a program to save a species with fewer than 200 individuals remaining in the wild, were evacuated on October 6, 36 hours, before less rare animals. Madagascar lemurs followed, then Asian elephants were prepared for sheltering in place in the most secure facility. The elephants sensed something wrong 12 hours before any evacuation began. They became agitated, trumpeting, refusing to enter their night houses. Their behavior matched reports from Sri Lanka before the 2004 tsunami, when elephants fled to high ground hours before the wave struck. Animals possess senses humans lack or have lost through evolutionary time. The elephants were detecting atmospheric changes too subtle for instruments or too complex for humans to interpret. They knew Milton was coming before weather forecasts became alarming. Harrison eventually sedated the elephants enough to move them to the secure facility, a bunker-like structure with walls 2 feet thick and a roof designed to withstand debris impacts. The elephants would survive there even if the rest of the zoo was destroyed. But watching them resist shelter, watching them trumpet warnings that no human could interpret, Harrison wondered what they sensed about Milton that forecasts weren't conveying. The elephants weren't just afraid. They were terrified in ways he'd never seen them before. Power companies across Florida mobilized the largest pre-positioning of restoration equipment in utility industry history. 40,000 utility poles, 8,000 miles of cable and wire, 3,000 transformers, 500 bucket trucks, all positioned just outside the expected damage zone, ready to move in the moment conditions allowed. The equipment came from utilities across the United States and Canada crews who would work 16-hour days for weeks after the storm. Living in temporary camps, sleeping in trucks, eating meals from mobile kitchens. The mutual aid agreements between utilities made this possible, but the scale exceeded anything previously attempted. Florida Power and Light's Emergency Operations Center coordinated restoration plans while the storm was still days away. Computer models predicted damage patterns based on wind speed, storm surge, and tree density. High-resolution mapping identified every pole, every transformer, every section of wire in the state, creating a digital inventory of infrastructure that would need repair or replacement. The models predicted catastrophic damage. In the direct impact zone, 90% of poles would fail. In adjacent regions, 50%. Across the entire affected area, 7 million customers would lose power, nearly half the state's population. Restoration would require weeks under optimal conditions. If subsequent storms arrived before repairs completed, the timeline could extend to months. The companies planned in stages. Critical infrastructure, first hospitals, water treatment plants, emergency services, then main distribution lines. Finally, individual neighborhoods and homes. The prioritization was logical but would create frustration. Residents watching repair crews drive past their darkened homes to work elsewhere wouldn't understand why their power remained out. But everyone involved knew the reality. Not everyone could be restored simultaneously. Some people would have power within days, others would wait weeks. A few those in areas with total infrastructure destruction might wait months while entire sections of the grid were rebuilt from scratch. Hospital intensive care units faced impossible decisions. Patients on ventilators require continuous power. Backup generators provide protection against normal outages, but Milton threatened to create conditions where hospitals themselves became unsafe structures, damaged by wind, flooded by surge, inaccessible for resupply or personnel relief. Hospitals in mandatory evacuation zones were ordered to transfer ICU patients to facilities outside the impact area. The transfers required ambulances equipped with portable ventilators, oxygen supplies, and medical personnel, capable of managing critically ill patients during transport. Each patient required a dedicated ambulance and medical team. Tampa General Hospital alone had 42 ventilator-dependent patients. Finding 42 ambulances and 84 paramedics or nurses to staff them, all while every emergency service in the state was mobilizing for storm response, strained resources beyond normal limits. The transfers began October 7th and continued until October 8th. Ambulance convoys, sometimes 10 vehicles long, traveled north on roads increasingly congested with evacuation traffic. Each convoy moved slowly, unable to use sirens or demand right-of-way because every vehicle on the road carried people fleeing for their lives. Some patients died during transfer, not from accidents, but from complications of their underlying conditions exacerbated by the stress of transport. The deaths were tragic, but expected. Medical protocols required documentation of informed consent. Patients or their families knew that transfer carried risks, but remaining carried certainty of inadequate care if the hospital lost power for extended periods. Neonatal intensive care units faced similar challenges. Premature infants, some weighing less than 2 pounds, required incubators maintaining precise temperature and humidity. They required feeding tubes, IV medications, continuous monitoring. Transporting them meant essentially building temporary mobile ICUs in ambulances. The youngest patients, 24-week premature twins, who had survived against odds and spent 6 weeks in NICU, were evacuated to Atlanta, 250 miles away. They survived the journey, but they wouldn't see their parents for 3 weeks after the storm because transportation back to Tampa remained difficult while infrastructure was restored. Milton forced families to choose between staying with critically ill loved ones or ensuring their own survival. Many chose to follow the ambulances, abandoning their homes to be with hospitalized family members in distant cities. They became evacuees and hospital visitors simultaneously, refugees from their own state. 19 prison facilities lay in mandatory evacuation zones. Prisoners can't evacuate themselves. They require secure transport to secure facilities, a logistical nightmare when the receiving facilities must accommodate additional inmates while maintaining security protocols. Florida's Department of Corrections activated emergency transfer plans. Buses, not standard civilian buses but armored vehicles with reinforced construction and security features, transported inmates from coastal prisons to facilities in central and northern Florida. Each bus carried 40 inmates supervised by 8 guards, a ratio 5 times higher than normal transport operations. The transfers created temporary overcrowding in receiving facilities. Prisons designed for 1,000 inmates suddenly housed 1,500. Gyms became dormitories. Recreation yards became dining areas. Inmates slept in shifts because insufficient bunks existed for everyone simultaneously. Security challenges multiplied. More inmates meant more potential conflicts, more supervision requirements, more complexity in managing feeding, medical care, and basic operations. Correctional officers worked 12-hour shifts for days, catching sleep in offices between shifts, and then there were decisions about which inmates to evacuate first. Maximum security prisoners required the most resources to transport and house safely. Minimum security inmates could be managed with less supervision, but some maximum security inmates had medical conditions that required them to be evacuated early. The prioritization created uncomfortable ethical questions. Should violent offenders with medical needs receive priority over non-violent offenders who are healthy? Should all inmates receive equal protection, or should some be deprioritized to ensure sufficient resources remained for evacuation of law-abiding civilians? The official answer was clear. All inmates receive equal protection under the law. The practical reality was more complex. Some inmates from minimum security facilities in the direct impact zone were temporarily released, their sentences suspended with instructions to report to different facilities after the storm passed. This freed resources for evacuating inmates who couldn't safely be released. Most reported as instructed after the storm. A few didn't, becoming fugitives whose escape occurred not through dramatic prison breaks, but through administrative decisions forced by a hurricane. The National Weather Service issued a warning at 0400 hours on October 9th that used language never before included in official hurricane forecasts. Unsurvivable storm surge. Every word in weather warnings is carefully chosen, reviewed by meteorologists and communication specialists to ensure accuracy and clarity. The word unsurvivable had never appeared in hurricane products. Forecasters typically described surge heights 10 feet, 15 feet, 20 feet, and let the numbers convey danger. But numbers weren't sufficient for Milton. Computer models predicted surge exceeding 25 feet across portions of Tampa Bay. Buildings would be underwater to their second or third floors. Barrier islands would be completely submerged. Anyone who remained in the surge zone would almost certainly die. Unsurvivable was the truth, stated bluntly, abandoning measured professional language for brutal honesty. The warning's author, senior forecaster David Martinez, later explained his reasoning. People have survived 15-foot surge before. They've survived 20-foot surge in specific locations with tall buildings. But no one survives being underwater in a 3-story building while wave action destroys the structure around them. It's not survivable. We needed to say that clearly. The warning's language drew criticism from some who felt it was too alarmist, too likely to cause panic. But panic in the sense of irrational behavior never materialized. Instead, the warning appeared to finally convince holdouts who had resisted previous evacuation orders. Emergency managers reported that evacuation rates in the final 24 hours before landfall exceeded any previous hurricane. The warning worked because it respected the audience's intelligence, while conveying honest danger. It didn't exaggerate. It didn't use euphemisms. It stated a fact. If you remain in these areas, you will die. Approximately 98% of residents in the mandatory evacuation zones left. The 2% who remained included people too ill to travel, people caring for them, and a small number who refused orders despite understanding the risk. Emergency responders marked the homes of those who stayed with paint, a grim notation indicating that recovery teams would need to search these locations after the storm for survivors or bodies. By October 8th, the evacuation was largely complete. Roads that had been rivers of taillights fell quiet. Cities that normally hummed with activity became ghost towns. Along the coast, empty buildings waited. Shutters covered windows. Doors were taped to protect against pressure changes that could blow them open. Valuable possessions had been moved to second floors or taken away entirely. What couldn't be moved or protected was simply left, owners hoping it would survive but preparing for loss. The cities looked abandoned but weren't entirely empty. Emergency personnel, police, firefighters, emergency managers remained in hardened facilities, ready to respond during the brief calm of Milton's Eye when rescue attempts might be possible. They knew they were risking their lives. They stayed because others' lives might depend on them. News crews remained, broadcasting from fortified positions, documenting the storm for audiences watching from safe distances. Their presence was controversial. Some argued they encouraged risk-taking by example. Others defended their role in providing real-time information that could save lives if unexpected conditions developed. Everyone who stayed understood they were gambling. Milton might weaken before landfall. The track might shift slightly, sparing some areas while devastating others. Surge predictions might overestimate actual inundation. Any of these possibilities might justify the decision to remain, but Milton didn't weaken. The track held steady, and surge predictions, if anything, underestimated what would come. The evacuation succeeded in its primary goal. When Milton made landfall, 2.8 million people who would have been in extreme danger were safely inland. Gridlock and confusion were inevitable, given the scale. Supplies ran short. People spent uncomfortable nights sleeping in cars. Gas stations struggled to meet demand. The system strained nearly to breaking. But it held. No evacuation-related deaths occurred. No highways collapsed under the traffic load. No mass casualties resulted from accidents or exposure during the exodus. The evacuation demonstrated something important. Modern civilization, despite its complexity, can still execute large-scale coordinated actions when danger demands. 2.8 million people moving in organized fashion over 72 hours represents a triumph of planning, infrastructure, and social cooperation. It also demonstrated something concerning, that evacuation worked because the warning time was sufficient. 72 hours from the moment the evacuation was ordered until landfall. 3 full days to move millions of people. Milton intensified so rapidly that forecasters nearly didn't have that time. If the storm had formed 12 hours later or intensified just slightly faster, the evacuation might have been ordered with only 48 hours remaining. Roads would have been more congested. Resources would have been more strained. Some percentage of the population wouldn't have escaped in time. The margin of success was narrower than anyone wanted to acknowledge. And the troubling question, what happens when the next Milton forms? What happens when forecasters issue evacuation orders with confidence because models show clear danger, but people remember the difficulty of this evacuation and decide to take their chances by staying? Every successful evacuation plants seeds of complacency. We evacuated last time and the storm wasn't as bad as predicted, becomes rationalization for not evacuating next time. The lottery of hurricane strikes means most evacuations will seem, in hindsight, like overreactions. Only the rare direct hits validate the effort and cost. But hurricanes are lotteries where losing means death. The stakes force conservative decision-making. Evacuate even when uncertain. Prepare for the worst even if the most likely outcome is less severe. Milton tested whether modern society could organize and execute the largest hurricane evacuation in history. We passed that test, but the test revealed how close we came to failure and how little margin remains for error as storms grow more intense and evacuations grow more difficult. The race against the wind was won. Barely. And the next race approaches faster than anyone anticipated. At the European Centre for Medium-Range Weather Forecasts in Reading, England, quantum computers process 18 petabytes of Milton data every hour. 18 petabytes. 18 million gigabytes. If stored on standard hard drives, the data would fill a warehouse. The quantum processors operating on principles of superposition and entanglement that seem more magic than physics digest this torrential flow of information, searching for patterns invisible to classical computation. The data streams arrive from satellites measuring ocean temperature, atmospheric humidity, wind speed at multiple altitudes, infrared radiation indicating cloud top temperatures, and a dozen other parameters. Ground stations contribute surface pressure, rainfall rates, lightning frequency. Hurricane Hunter aircraft transmit real-time measurements from inside the storm. Ocean buoys, those that haven't failed, report wave heights and subsurface temperatures. Each data source produces thousands of measurements per second. Combined, they create a four-dimensional, the map of Milton's structure, evolving moment by moment 3 spatial dimensions, plus time, captured in numbers that must be processed faster than they arrive, or the analysis falls hopelessly behind reality. The quantum computers handle this computational avalanche, running ensemble forecasts hundreds of simulations simultaneously, each starting with slightly different initial conditions, each producing slightly different futures. The spread of outcomes indicates forecast uncertainty. When simulations agree, confidence is high. When they diverge, the forecast becomes ambiguous. For Milton, something unprecedented happens. The simulations don't just agree on intensity and track, they converge on internal storm structure. Multiple runs independently predict that Milton will develop 6 mesovortices arranged in hexagonal pattern. They predict temperature inversions at specific altitudes. They predict electromagnetic signatures matching observed values. The models aren't just forecasting weather. They're predicting storm physics that no models have successfully simulated before. The breakthrough comes from pattern recognition algorithms originally developed for analyzing quantum mechanics experiments. These algorithms search for correlations, statistical relationships between measurements that might indicate underlying structure. Applied to Milton, they discover something remarkable. The storm generates atmospheric gravity waves that propagate outward at predictable frequencies. Atmospheric gravity waves aren't like ocean waves. They're oscillations in air density, pressure, and temperature that ripple through the atmosphere when air parcels displaced vertically try to return to equilibrium. Thunderstorms generate them. Mountain ranges generate them. Large weather systems generate them. But Milton's gravity waves show structure that ordinary storms don't produce. They propagate in concentric rings, their wavelengths and frequencies related by simple mathematical ratios 2:1, 3:1, 5:3. The ratios resemble harmonics in music, where notes relate through simple frequency relationships. The gravity waves from Milton create a signal that can be detected thousands of miles away. Sensitive barometers in Hawaii record pressure oscillations, matching Milton's fundamental frequency. Stations in Alaska detect harmonics. The storm is broadcasting its structure through the atmosphere, sending information that propagates at the speed of sound, about 700 miles per hour at sea level. The signals circle the globe in 96 hours. By the time Milton dissipates, Its gravity wave signature has propagated through the entire atmospheric envelope, creating pressure perturbations measurable on every continent. The discovery has profound implications. If storms generate unique gravity wave signatures, those signatures could be used to infer storm structure remotely. No need for hurricane hunter aircraft to fly through every storm. Just listen to the atmospheric frequencies they broadcast. But deeper questions remain. Why does Milton generate harmonic signatures while other storms produce random frequencies? Is the harmonicity coincidental, or does it indicate some form of resonance, the storm finding natural frequencies of the atmosphere and amplifying them? We don't know. But we're learning that hurricanes communicate not just through obvious signals like wind and rain, but through subtle atmospheric oscillations that carry information across planetary distances. The electromagnetic pulses that Milton generates don't remain confined to the storm. They propagate through Earth's magnetic field, coupling with the ionosphere, that layer of charged particles beginning 50 miles above the surface. The coupling creates Whistler waves, electromagnetic oscillations that propagate along magnetic field lines, traveling from one hemisphere to the other. Ground stations in New Zealand detect whistlers originating from Milton. The signals arrive seconds after lightning strikes in the storm, having traveled through the magnetosphere, the region of space controlled by Earth's magnetic field, at nearly the speed of light. The whistlers sound like falling tones when converted to audio, starting at high frequencies and sweeping downward, creating an ethereal descending whistle. Amateur radio operators report these whistlers interfering with communications. The signals aren't strong, measuring microwatts of power by the time they reach receivers thousands of miles away, but they occur continuously while Milton rages, creating persistent background noise across multiple frequency bands. The whistlers affect more than radio. They interact with Van Allen radiation belts, regions of charged particles trapped by Earth's magnetic field. The interactions cause particles to precipitate into the atmosphere, creating aurora-like glows visible from Cuba despite being far from the Arctic or Antarctic regions where aurora normally occur. Satellite operators notice anomalies in spacecraft electronics, correlating with Milton's electromagnetic activity. The anomalies don't cause failures but trigger error correction systems, creating additional workload for flight computers. Some satellites switch to backup systems automatically, responding to conditions they interpret as radiation threats. Military networks monitoring electromagnetic spectrum detect signals matching nuclear electromagnetic pulse signatures. The signals trigger alerts that require human verification before escalating to emergency protocols. Operators quickly determine the source is Milton, not nuclear detonations, but the incident reveals that hurricanes can generate electromagnetic effects mimicking artificial threats. The storm doesn't just affect local weather. It creates electromagnetic disturbances that reach into space, affect satellite operations, and trigger military warning systems designed to detect completely different threats. Artificial intelligence systems monitoring hurricane behavior identify something unexpected. Cyclone 7, a neural network trained on decades of satellite imagery and storm observations, analyzes Milton's evolution. The system has learned to recognize patterns humans might miss, finding correlations in high-dimensional data that exceed human cognitive capacity. Cyclone 7 reports that Milton generates acoustic signatures in the ocean that propagate through underwater mountains and are detectable near Antarctica. The system identifies this pattern by analyzing hydrophone data and correlating it with satellite observations of ocean surface conditions. The acoustic signatures result from a phenomenon called stormquakes, rhythmic pulses created when waves pound coastlines or ocean floor topography in synchronized patterns. Normal storm waves arrive randomly, each creating small seismic signals that don't add coherently. But Milton's organized eye wall generates waves that arrive with consistent spacing, creating pulses that add constructively. The pulses propagate through ocean crust as sound waves, traveling thousands of miles. Underwater mountains, seamount chains, and mid-ocean ridges act as waveguides, channeling the sound along specific paths. Some energy travels so efficiently that signals originating in the Gulf of Mexico reach hydrophones in the South Atlantic with minimal attenuation. Marine mammals detect these signals. Whale populations in the South Atlantic modify their migration patterns in response to acoustic signatures from storms in the Caribbean, changing course days before those storms could directly affect their locations. The whales are responding to precursors, to signals indicating that distant ocean conditions may soon affect them. Cyclone 7 identifies these correlations but doesn't explain them. AI systems excel at pattern recognition but struggle with causation. The system can tell us that whales respond to storm acoustics, but not why this behavior evolved or what specific information the whales extract from the signals. We're left with observations that raise more questions than they answer. Why do hurricanes create such long-range acoustic signatures? What information do those signatures contain? How do marine mammals interpret signals that travel thousands of miles through ocean and crust? Milton spawns 127 tornadoes in 6 hours. Hurricanes commonly produce tornadoes, usually brief, weak events forming in outer rain bands where wind shear creates rotation. Milton's tornadoes are different. Many achieve EF2 or EF3 intensity, with winds exceeding 130 miles per hour. Some persist for 20 minutes or more, far longer than typical hurricane-spawn tornadoes. The tornadoes form not just in outer bands, but within the eye wall itself, a location where tornadoes should be impossible because the rotational wind speeds are already so extreme. Yet Doppler radar detects distinct rotation signatures within the eye wall, vortices measuring hundreds of meters across, with wind speeds exceeding the surrounding eye wall by 50 miles per hour. Each tornado carries chemical signatures from high altitudes. Air samples collected after the tornadoes dissipate contain ice crystals and salt particles from Milton's upper eye wall, evidence that these vortices extended from surface to 40,000 feet altitude, connecting ocean and stratosphere through rotating columns of air. The tornadoes deposit ocean water hundreds of miles inland. Salt crystals appear in rainfall over Georgia and South Carolina, carried by tornadoes that formed over the Gulf and persisted long enough to transport material across the Florida peninsula. The salt won't fall immediately. It will remain suspended in the atmosphere for weeks, gradually settling onto vegetation, freshwater lakes, agricultural fields. The ecological consequences will appear over months. Salt-sensitive plants will show stress. Freshwater ecosystems will experience temporary salinity increases. Agricultural soils will require remediation. Milton doesn't just damage through wind and surge, it redistributes ocean chemistry across entire ecosystems, creating impacts that persist long after the storm dissipates. NASA's atmospheric chemistry satellites detect something unprecedented in the stratosphere above Milton. New molecules, combinations of water, ozone, and cosmic ray particles that have never been observed naturally. The molecules exist for only microseconds before breaking apart, but during their brief existence, they catalyze reactions that wouldn't otherwise occur. The chemistry happens because Milton's updrafts inject water vapor into layers that should remain bone dry. The stratosphere, the atmospheric layer, extending from about 35,000 to 160,000 feet, is normally a desert, with humidity below 1%. Water doesn't reach these altitudes because it freezes out at lower levels, but Milton's updrafts are powerful enough to shoot water past the freezing zone before it can fully crystallize. Ice particles carried to 40,000 feet, then 50,000 feet, then 60,000 altitudes, where normal clouds never form. At these heights, cosmic rays, high-energy particles from space constantly bombard the atmosphere. When they encounter ice particles containing trace impurities, they trigger exotic chemistry. Water molecules break apart, recombine, form radicals that react with ozone. The result? Temporary holes in the ozone layer directly above the hurricane. The holes measure thousands of square miles, allowing increased ultraviolet radiation to reach the surface. They persist for days after the storm passes, slowly refilling as atmospheric transport brings ozone-rich air from surrounding regions. But while the holes exist, UV levels beneath them increase by 20 to 30%. That's enough to cause sunburn in half the normal time. It's enough to stress plankton in surface waters, potentially affecting marine ecosystems. It's enough that public health officials issue sun safety warnings for regions hundreds of miles from the storm. Milton doesn't just affect tropospheric weather, the weather we experience at ground level. It reaches into the stratosphere, creating chemistry that affects how much solar radiation reaches Earth's surface. The storm's electromagnetic field affects bird navigation across the Caribbean and southeastern United States. Birds migrating through the region experience errors in their internal compasses, the magnetoreception systems that allow them to sense Earth's magnetic field and use it for navigation. The errors don't completely disable navigation. Birds have backup systems using visual landmarks, stellar cues, even olfactory information. But the magnetic disruption causes deviations. Flocks that should arrive in Venezuela appear in Colombia, 500 miles west of their intended destination. Birds tracked by satellite transmitters show zigzag flight paths instead of straight lines, as if constantly correcting course but unable to maintain accurate headings. The deviations persist for weeks after Milton passes. Birds don't just experience temporary confusion during the storm, the atmospheric chemistry changes. Milton creates apparently leave residual effects that interfere with magnetoreception. The mechanisms remain unclear, but the correlation between storm-modified atmospheric conditions and bird navigation errors is statistically significant. Some bird populations will fail to reach their destinations. Migration delays mean arriving after optimal breeding times or after food resources are exhausted. Energy spent correcting navigation errors leaves birds in poorer condition, reducing survival rates. For endangered species already living on population, margins, even small additional mortality, can threaten long-term viability. Milton's impacts extend beyond the immediate destruction of wind and surge. The storm creates electromagnetic and chemical perturbations that affect biological systems across a continent, creating cascading effects that will take years to fully manifest. The storm generates standing waves in Earth's magnetic field. These aren't waves in the usual sense, not propagating oscillations, but stationary patterns where magnetic field strength varies periodically in space. Standing waves appear when waves propagating in opposite directions interfere, creating nodes where amplitudes cancel and antinodes where they amplify. Milton creates these patterns through its rotation. The storm's electromagnetic field rotates with the eye wall, sweeping past any fixed observation point once every 6 minutes. To a stationary observer, the field appears to oscillate with that 6-minute period, but the field doesn't remain local. Magnetic disturbances propagate through Earth's magnetosphere, the region where Earth's magnetic field dominates over the solar wind. Disturbances from Milton couple with the magnetosphere's natural oscillation frequencies, creating resonances that amplify specific patterns. Satellites designed to measure Earth's magnetic field detect these resonances as variations in field strength that persist for hours after the storm passes. The variations are small, less than 1% of the total field, but measurable and definitely anomalous. The standing waves appear as aurora-like phenomena visible from Cuba and the Bahamas. Normally, aurora occur only at high latitudes, where Earth's magnetic field funnels solar wind particles into the atmosphere. But Milton's magnetic disturbances create temporary field configurations that allow charged particles to reach lower latitudes. The glows are subtle, requiring dark skies and sensitive cameras to capture, but they're real. For a few hours on October 9th, The skies over the Caribbean shimmer with faint curtains of light, green and red, dancing in response to a hurricane rather than the solar wind. Atmospheric physicists studying these phenomena realize that storms can create conditions mimicking space weather effects. The implications are significant. If hurricanes generate magnetic disturbances that affect satellite electronics and create aurora-like displays, they're coupling atmospheric and space physics in ways we haven't appreciated. The boundary between weather and space weather isn't as clear as we thought. Stormquake seismic pulses generated by wave action reveal hidden underwater topography. The pulses propagate through ocean crust, reflecting and refracting from underwater mountains, valleys, and faults. Seismometers, designed to detect earthquakes, capture these reflections, creating an unintentional sonar survey of ocean floor structures. Geophysicists analyzing the data discover previously unmapped seamounts in the Gulf of Mexico. The seamounts rise several thousand feet from the abyssal plain, but remain below sea level, invisible to ships but detectable through their effects on seismic wave propagation. The discovery is accidental, a byproduct of monitoring Milton rather than intentional geological survey, but it demonstrates that hurricanes can serve as natural seismic sources, illuminating subsurface structure through their generated waves. The technique could be used deliberately. Instead of deploying expensive seismic ships with air guns to survey ocean floors, we could use storm-generated waves as free seismic sources. The challenge is that we can't control when or where hurricanes occur, making systematic surveys difficult. But for regions prone to hurricanes, opportunistic data collection during storms could supplement traditional surveys. More fundamentally, the discovery reveals that hurricanes affect not just atmosphere and ocean surface, but the solid earth beneath. The coupling extends deeper than anyone suspected. Storm waves create pressure pulses that propagate kilometers into ocean crust, reflecting from geological structures, creating signals detectable hundreds of miles away. Earth's systems, atmosphere, ocean, crust, aren't separate but interconnected, communicating through processes that span scales from millimeters to thousands of kilometers. The isotope signatures in Milton's rainwater reveal not just where water came from but how it traveled through the storm. Different parts of the hurricane deposit rain with distinct isotope ratios. The eye wall produces rain enriched in heavy isotopes, oxygen-18 and deuterium, because only the heaviest water molecules can survive the extreme conditions there. Lighter molecules evaporate preferentially, leaving heavy isotopes concentrated in remaining liquid. Outer rain bands deposit lighter rain enriched in oxygen-16 and regular hydrogen, because water in these regions hasn't experienced the extreme evaporation and condensation cycles of the eye wall. By mapping isotope ratios across the storm's footprint, researchers create a picture of internal circulation. They can trace air parcels from their entry point in outer bands through their journey toward the eye wall, watching how isotope ratios evolve as water cycles through condensation and evaporation dozens of times. The maps reveal asymmetries that forecast models don't predict. The strongest updrafts occur not uniformly around the eye but concentrated in specific sectors. The downdrafts, where air descends from high altitudes, bringing dry stratospheric air into the lower atmosphere, show similar concentration. These asymmetries shouldn't be stable. Turbulence should smooth them out, creating uniform distributions. Yet they persist for hours, suggesting that Milton has internal structure beyond simple rotation, who preferred pathways where air rises and descends, regions of enhanced circulation that remain fixed relative to the storm center, even as the entire system rotates. The structure resembles a machine more than natural chaos. Not a machine in the sense of artificial construction, but in the sense of organized components working in coordination. The mesovortices feed the main circulation. The updrafts transport energy vertically. The downdrafts bring dry air that mixes with the eye wall, modulating intensity. It's functional, optimized, as if the storm has discovered configurations that maximize energy transfer and minimize dissipation. Chemical reactions in Milton's eye wall create trace gases that will influence cloud formation globally for years. The reactions occur because extreme conditions, temperature, pressure, electric fields, create environments where molecules that normally don't interact suddenly can. Nitrogen combines with oxygen, creating nitrogen oxides that rain into the ocean and will eventually affect marine chemistry. Ozone breaks down into reactive oxygen species that catalyze organic molecule formation. Water reacts with cosmic ray particles, creating short-lived radicals that trigger chain reactions. Most of these molecules exist for only seconds before reacting further or breaking apart, but some persist long enough to be transported out of the storm and into the general atmospheric circulation. They become seeds for cloud formation nucleation sites, where water vapor can condense more easily than on natural aerosols. The enhanced nucleation will increase cloud cover slightly over regions downwind of Milton for months or years. The increase is small fractions of a percent, but measurable. And because clouds affect how much solar radiation reaches the surface, the change will influence regional climate. It's a feedback loop. The storm creates conditions that lead to more clouds. More clouds mean less solar heating of the surface. Less heating might mean slightly lower sea surface. Temperatures. Lower temperatures make future storms slightly less likely to reach Milton-level intensity, or the feedback might work differently. More clouds could trap heat radiated from Earth's surface, leading to warming rather than cooling. Warmer surface waters could make future rapid intensification more likely. The sign and magnitude of the feedback remain uncertain, but the existence of the feedback is clear. Storms don't just respond to climate. They affect climate through chemical signatures that persist long after the storms dissipate. Milton will influence weather years from now through chemistry we're only beginning to understand. Quantum computers at the European Centre continue processing data days after Milton dissipates. The processors aren't just analyzing what happened, they're searching for precursors, signals that appeared before the storm intensified, patterns that might allow earlier warning of rapid intensification events. The search identifies candidates. 6 hours before intensification began, satellite microwave measurements detected subtle changes in ocean surface roughness. 3 hours before intensification, lightning rates increased in thunderstorms that would later organize into the eye wall. 1 hour before, atmospheric gravity waves showed frequency shifts suggesting structural reorganization. Each signal alone would be dismissed as noise-random variation within normal parameters, but together they form a pattern. The pattern doesn't guarantee intensification will occur, but its presence increases probability significantly. The discovery suggests early warning might be possible, not certainty, but improved odds. Instead of recognizing rapid intensification only when it's already happening, forecasters might detect it 6 or 12 hours earlier. 12 hours might not seem like much, but in hurricane forecasting, where decisions about evacuations and resource deployment must be made with incomplete information, 12 additional hours is transformative. It's the difference between evacuating safely and fleeing in panic. It's the difference between pre-positioning emergency supplies and having them arrive after they're needed, but the signals require quantum computing to detect. Classical computers can't process the data volumes or identify the high-dimensional patterns involved. The early warning capability depends on technology that's expensive, rare, and not available to most forecasting centers. We're developing the ability to see further into the future, but that ability depends on computational resources that remain scarce. The question becomes, how do we deploy early warning systems globally when the technology exists in only a handful of facilities? The signals in the storm tell stories about physics, biology, chemistry, geology, all disciplines connected through the common thread of Milton's energy. The storm generated gravity waves that circled the globe. It created electromagnetic disturbances reaching into space. It spawned tornadoes carrying ocean salt hundreds of miles inland. It triggered chemical reactions producing molecules that will influence climate for years. It generated seismic waves revealing hidden geology. It affected bird navigation, whale migration, atmospheric chemistry, and magnetic fields. Every signal carries information. Not information in the human sense, not messages or meaning, but physical information. Correlations between measurements, patterns in data, structure that emerges from chaos. Reading those signals requires instruments, algorithms, computers powerful enough to find patterns in petabytes of data, but also requires recognizing that hurricanes aren't isolated weather events. They're phenomena that couple atmosphere, ocean, crust, and magnetosphere that affect biology and chemistry that leave fingerprints detectable across multiple scientific disciplines. We've spent centuries studying weather as if it's separate from other Earth systems. Milton demonstrates that separation is artificial. The storm is atmospheric, oceanic, geological, chemical, electromagnetic, biological. Understanding it requires integration across disciplines that normally don't communicate. The signals in the storm are teaching us that Earth is more interconnected than we imagined, and that our traditional boundaries between scientific fields are constructs that nature doesn't recognize. Milton spoke in many languages simultaneously. We're only now learning to listen. 6 weeks after Milton dissipates, oceanographers return to the Gulf of Mexico to survey what the storm left behind. They find a new current, not a temporary eddy that will fade in weeks, but a persistent circulation pattern, a river within the ocean, measuring 50 miles wide and extending from surface to depths of 1,500 feet. The current flows in a direction perpendicular to prevailing patterns, cutting across the loop current that has defined Gulf circulation for millennia. The new current carries water displaced by Milton's passage, massive volumes transported by the storm's circulation and deposited in locations where they create density gradients. Those gradients drive flow that will persist for years, gradually weakening but remaining detectable until the next major storm reorganizes ocean structure again. Computer models attempting to simulate Gulf circulation now must include this feature. Forecasters predicting future hurricanes must account for how this altered circulation will affect storm development. Fisheries managers must understand how the current redistributes nutrients and marine life. The storm didn't just pass through, it permanently modified the ocean environment. This is what climate scientists mean when they say we're entering a new regime. Not just more intense storms, but storms that leave lasting changes. Storms that accumulate, each building on modifications created by the last, pushing a system further from historical states. Milton's legacy will influence the next decade of hurricane activity in the Gulf, and by the time that influence fades, other storms will have created their own legacies, their own persistent circulation patterns, their own reorganizations of ocean structure. Climate models project 50 Milton-class hurricanes by 2050, 50 hypercane storms with winds exceeding 190 miles per hour and central pressures below 900 millibars occurring over the next 26 years. Not spread uniformly, but clustering when conditions align favorably, perhaps 3 or 4 in a single season followed by years with none. The projection assumes moderate greenhouse gas emissions, neither the most optimistic scenario, where aggressive mitigation reduces warming, nor the worst case where emissions accelerate. Under moderate emissions, global temperatures increase by 2 to 3 degrees Celsius above pre-industrial levels by mid-century. Ocean heat content continues rising. The depth of warm water accessible to hurricanes expands, and hypercanes transition from once-per-century events to once-per-decade occurrences, perhaps once every 5 years, perhaps even more frequently if feedback mechanisms not yet included in models amplify warming beyond current projections. 50 Milton-class storms means 50 Tampa Bay-scale evacuations, 50 infrastructure-destroying events, 50 economic shocks measuring tens of billions of dollars each. The cumulative impact exceeds what coastal regions can absorb while maintaining their current form. Cities will adapt, or they will empty. There's no third option. Miami begins construction on seawalls 90 feet high, not the traditional seawalls that line waterfront parks, decorative barriers designed to prevent erosion while allowing beach access. These are fortress walls, engineered structures with footprints measuring hundreds of feet, designed to withstand Category 6 hurricanes, a classification that doesn't officially exist yet, but that engineers now design for anyway. Category 6, sustained winds exceeding 200 miles per hour, storm surge exceeding 30 feet, conditions that no existing structure was built to withstand. The walls will cost billions. They'll permanently alter Miami's relationship with the ocean, blocking views, restricting access, transforming waterfront property from desirable to depressing. But they'll also allow the city to survive in an era when storms like Milton become routine. Other cities make different choices. Charleston, South Carolina begins elevating infrastructure, raising roads, relocating utilities to higher ground, requiring new construction to have first floors 15 feet above current sea level. The changes create cities that look dystopian, roads serpentining upward to pass over infrastructure, buildings perched on stilts like houses in flood-prone regions of Southeast Asia. New Orleans, already below sea level and protected by levees, undertakes the largest civil engineering project in United States history. The existing levee system proved inadequate during Hurricane Katrina in 2005. Milton-class storms would overwhelm it completely. The new system will cost over $100 billion and require 20 years to construct. It might not be completed before the next catastrophic storm strikes. Boston explores floating neighborhoods, sections of the city built on platforms that rise and fall with sea level, remaining habitable even when surrounding areas flood. The technology exists. Floating homes are common in the Netherlands, but scaling it to city block dimensions poses engineering challenges that remain unsolved. Every coastal city faces the same calculation: how much to invest in protection versus how much to invest in relocation. Neither option is affordable. Both are necessary. Agricultural zones shift northward at 3 miles per year. That's the rate at which optimal growing conditions for major crops move poleward as climate warms. Corn production that dominated Iowa begins migrating into Minnesota and southern Canada. Wheat belts shift from Kansas toward the Dakotas. Cotton moves from Georgia into Virginia. But it's not just temperature that's changing. Rainfall patterns reorganize as storms like Milton redistribute water in ways that have no historical precedent. Regions that received reliable summer rains now experience droughts. Areas that were arid develop regular storms. The reorganization happens faster than agriculture can adapt. Farmers accustomed to specific rainfall patterns find those patterns vanishing. Irrigation systems designed for historical water availability become inadequate or obsolete. Crops selected for regional conditions suddenly face environments they weren't bred for. Some regions become more productive. Longer growing seasons and increased CO2, which enhances plant growth, create opportunities in places that were previously marginal for agriculture. Parts of Canada and Siberia transform from borderline farmland into prime agricultural zones. But these gains don't offset losses. Productive farmland in current breadbasket regions degrades faster than new farmland develops. Soils in newly favorable regions lack the centuries of development that make current farmland productive. Infrastructure, roads, storage facilities, processing plants, exists where farms used to be, not where they're moving to. Global food production doesn't collapse, but it becomes less reliable. Yields vary more from year to year. Prices spike unpredictably. Countries that once exported grain become importers. Supply chains reorganize, creating political tensions as nations compete for declining surpluses. And the storms keep coming, each one disrupting agriculture across multiple states, each one forcing recalculation of what can be grown where. Insurance companies abandon coastal coverage entirely, not gradually, not with reluctant retreat from specific high-risk areas. The withdrawal is sudden and comprehensive. After Milton, after calculating the losses from insuring homes that are destroyed, insurers collectively decide that coastal property has become uninsurable at premiums customers can afford. The market simply disappears. Homeowners who have paid insurance premiums for decades find their policies non-renewed. New buyers can't obtain mortgages because lenders require insurance that no company will provide. Property values collapse not from storm damage but from the impossibility of financial protection. Governments step in, creating insurance programs of last resort. These programs offer coverage but at premiums reflecting actual risk costs that exceed what most homeowners can pay. A typical house in a high-risk zone might require $50,000 annual premium for adequate coverage. Few can afford it. The government programs become trillion-dollar liabilities. Every major hurricane triggers payouts that dwarf premium collections. Taxpayers in inland states subsidize coastal residents who refuse to relocate. Political tensions rise. Legislators from non-coastal states demand an end to subsidies. Coastal representatives argue that abandoning coastlines means abandoning major population and economic centers. No consensus emerges. The programs continue, growing more expensive each year, their unfunded liabilities ballooning toward incomprehensible numbers. Future generations will inherit this debt, payment for decisions made decades earlier to develop coastlines that couldn't sustain development long-term. Milton's contribution to this crisis, proving that the previously uninsurable could actually occur. Before Milton, insurers could claim that worst-case scenarios were theoretical. After Milton, the worst case had been demonstrated. The risks were no longer hypothetical. Cities, like Houston, transform into amphibious municipalities. The concept sounds like science fiction. Buildings designed to float during floods, remaining habitable even when ground floors are underwater. But the technology exists and is being deployed. Structures are built on platforms that rest on vertical pillars when water levels are normal. When floods arrive, the platforms float upward, guided by those same pillars, rising with the water until it recedes. Inside, residents continue their lives, experiencing floods as temporary elevation changes rather than catastrophic inundations. The transformation requires rebuilding cities from foundations upward. Existing buildings must be retrofitted or demolished and replaced. Infrastructure, roads, utilities, communications must be designed to function whether above or below water. The cost is astronomical, but the alternative, abandoning cities with millions of inhabitants, is economically and politically impossible. Houston begins the conversion in 2028, starting with flood-prone neighborhoods near Buffalo Bayou. By 2035, substantial portions of the city have been converted. The skyline remains recognizable, but the relationship between buildings and ground has changed fundamentally. The city floats, sometimes literally. Other cities follow. Bangkok, already sinking and flood-prone, becomes a test case for how rapidly conversion can occur. Venice, dealing with Aqua Alta for centuries, modernizes its approach, installing systems that allow the entire historic city center to rise with sea level. Jakarta begins a 50-year project to make Indonesia's capital amphibious before it drowns completely. The solutions are expensive, technically challenging, and require maintenance that will continue forever, but they allow cities to persist in locations that would otherwise become uninhabitable. Whether this represents adaptation or futile resistance to inevitable relocation remains debated. The Arctic opens to shipping as storms like Milton accelerate ice melt. The mechanism is indirect but powerful. Hypercanes create ocean mixing that extends to depths of thousands of feet, bringing warm water to the surface where it can absorb solar radiation more efficiently. That absorbed heat doesn't remain local. Ocean currents transport it globally, including to polar regions where it accelerates ice melt. The Arctic, which once required icebreakers for navigation most of the year, becomes ice-free during summers by 2040. Shipping routes that were impassable become viable alternatives to Panama and Suez canals. Travel time between Asia and Europe drops by thousands of miles. The economic implications are enormous, but the new routes aren't safe. Hypercanes, which once occurred only in tropical and subtropical regions, begin forming at higher latitudes as those regions warm. The Arctic experiences its first hurricane in 2043, a storm that forms over unusually warm water northeast of Iceland and tracks across the Norwegian Sea with winds exceeding 150 miles per hour. Ships attempting to use Arctic routes must now account for storms that have no historical precedent in those regions. Rescue infrastructure doesn't exist. If ships encounter trouble, help might be days away too far to reach crews in distress. Early voyagers accept these risks, drawn by profit opportunities. Some succeed, some don't. By 2050, Arctic shipping becomes routine but remains dangerous. It's the maritime equivalent of early aviation, clearly the future, but not yet reliable enough to be considered safe. And every Arctic hurricane accelerates ice melt further, creating feedback loops that push the system toward complete ice loss during summers. Once that threshold is crossed, the Arctic Ocean will absorb dramatically more solar radiation, accelerating warming in ways that models struggle to predict. Floating cities anchored in deep water begin construction in 2038. The concept, platforms measuring square miles in area, floating on the open ocean, home to tens of thousands of residents. The platforms rise and fall with waves and tides but remain stable through all but the most extreme conditions. When hypercanes approach, the cities either evacuate or ride out the storms, designed to survive. Category 7 winds sustained velocities exceeding 215 miles per hour. Category 7, the classification that the World Meteorological Organization reluctantly adds to the Saffir-Simpson scale in 2036. After storms exceeding Category 5, intensity become too common to classify them all as simply 5+. The floating cities aren't refuges from climate change. They're acknowledgements that some people refuse to abandon ocean living even as coastlines become uninhabitable. The cities offer a middle ground, ocean access without the vulnerability of fixed locations. When storms threaten, the platforms can be towed to safer locations or simply ride out conditions that would destroy land-based structures. The first city, New Atlantis, located 200 miles east of Miami in water, 3 miles deep, opens with 20,000 residents in 2042. Most are wealthy individuals seeking ocean views without hurricane risk. But the cities quickly attract others, researchers studying ocean systems, workers supporting offshore industries, people displaced from drowned coastlines who prefer ocean life to inland relocation. By 2050, 6 floating cities exist in the Atlantic, with 8 more under construction in the Pacific. Total population, 400,000 people living permanently on the open ocean. It's a tiny fraction of global population, but it represents a new form of human settlement civilization, adapting to an environment where traditional coastal living has become untenable. Mass climate migration moves 500 million people by 2040. 500 million. The population of North America. That's how many people relocate from regions that become uninhabitable, either due to storm exposure, heat extremes, water scarcity, agricultural collapse, or combinations of these factors. The migrations aren't organized evacuations. They're gradual movements over decades, as individuals and families decide their locations no longer offer viable futures. Some relocate within countries from coasts to interiors, from south to north, from lowlands to highlands. Others cross international borders, seeking regions where climate remains tolerable. The movements create political crises. Receiving regions struggle to absorb migrants, straining infrastructure, housing, social services. Competition for resources increases. Tensions between established residents and newcomers escalate. In some regions, the influx sparks violence. In others, it drives innovation as communities develop new approaches to integration. The migrations also redistribute human capital. Doctors, engineers, teachers, skilled workers, people who made coastal cities function relocate to interior regions. The coastal cities they leave lose not just population but the expertise needed to maintain complexity. Infrastructure fails not from lack of resources but from lack of people who know how to operate and repair it. Some regions benefit from migration. Declining populations in northern latitudes receive infusions of youth and labor. Cities in Canada and Scandinavia that were struggling with aging demographics suddenly have excess workers, but the benefits are uneven and the social disruptions are universal. By 2050, the geography of human civilization has been redrawn. Population centers that defined the 20th century, coastal megacities in tropical and subtropical regions, have lost half their inhabitants. New centers emerge in locations that were previously peripheral. The world map requires redrawing to reflect where people actually live. Humanity splits between those who retreat inland and those who adapt to life alongside monsters. This is perhaps the most profound change. Not the physical relocations, not the engineered solutions, but the psychological transformation. Previous generations saw hurricanes as exceptional events, disasters that disrupted normal life, but were fundamentally abnormal. Future generations will see hypercanes as normal. Children born in 2030 will come of age in a world where Category 6 hurricanes strike somewhere every year. They'll never know a time when storm seasons weren't existential threats to coastal populations. The adaptations that seem extreme to us, sea walls 90 feet high, amphibious cities, mandatory evacuations spanning millions of people, will be routine aspects of their reality. These children will develop different relationships with risk. They'll accept that some years will bring disasters, that some places will periodically become uninhabitable, that evacuation is normal rather than exceptional. The psychological orientation will be fundamentally different from previous generations who expected stability and treated disruption as aberration. But not everyone will adapt the same way. Some will embrace the challenge, developing technologies and strategies to thrive despite hyperactive storm systems. They'll create architecture designed for winds exceeding 200 miles per hour. They'll develop early warning systems that provide days or weeks of advance notice. They'll build economies around the boom-bust cycle of storm seasons, accepting periodic destruction as the price of coastal living. Others will retreat, deciding that life in storm zones isn't worth the risk regardless of available protections. They'll move inland, accepting reduced ocean access in exchange for security. They'll create new communities in regions that were previously underdeveloped, transforming interior zones into population centers. The split creates two populations with diverging experiences and worldviews. Those who stay coastal will develop cultures around storm preparedness, evacuation, and recovery. Those who move inland will lose that immediate connection to hurricanes, experiencing them as events affecting others rather than direct threats. Over time, these populations may diverge further, developing distinct identities based on their relationships with climate extremes. By 2050, the question isn't whether humanity can survive in a world with frequent hypercanes. It's what kind of humanity we become in the process. Do we become more cooperative, recognizing that climate extremes require unprecedented coordination? Or do we fragment further, with competition over resources overwhelming collaborative impulses? Do we maintain our technological capabilities, continuing to innovate and build despite repeated destruction? Or do we simplify, retreating to lower complexity systems that are more robust but less capable? Do we preserve coastal cities through massive engineering projects? Or do we accept that some locations can't sustain permanent habitation and focus on mobility instead? These questions have no predetermined answers. They'll be determined by choices made over coming decades, choices about investments, about policies, about values. Different regions will make different choices, creating a patchwork of approaches. Some cities will become fortresses, protected by engineering marvels that allow them to withstand anything storms produce. Others will become seasonal settlements, inhabited during calm months and evacuated during storm season. Still others will be abandoned entirely, left as ruins documenting an era when humans thought they could build permanent structures in places that nature periodically reclaims. The architecture of future coastal cities reflects lessons learned from Milton and its successors. Buildings no longer rise straight from ground to roof. They're designed in sections that can detach and be relocated when storms threaten. The ground floors are sacrificial, built to flood and be rebuilt, protecting upper floors where valuable equipment and permanent infrastructure reside. Roads are elevated on pylons, remaining passable even when ground-level flooding occurs. Utilities run through protected conduits that can withstand submersion. Power grids are distributed rather than centralized, ensuring that storm damage in one area doesn't cascade across entire regions. Most dramatically, critical facilities, hospitals, emergency services, government centers are built underground, not in basements vulnerable to flooding, but in deep bunkers excavated from bedrock, completely isolated from surface conditions. These facilities can continue operating for weeks without external support, providing continuity during and after storms. The aesthetic is stark. Future coastal cities look nothing like their predecessors. They're functional rather than decorative, engineered for survival rather than beauty. Visitors from inland regions find them unsettling, too industrial, too focused on disaster preparedness, lacking the vibrancy that characterized pre-Hypercane urban design. But residents adapt. They develop new forms of beauty within the constraints. Gardens are designed to be portable, moved indoors before storms. Art is created from materials that survive water and wind. Architecture celebrates structural honesty rather than hiding engineering behind facades. A new aesthetic emerges, the beauty of resilience, the elegance of systems designed to endure. Agricultural systems transform as storms redistribute rainfall and nutrients across unprecedented scales. The concept of stable growing seasons, spring planting, summer growth, fall, harvest breaks down when violent storms can arrive any month, destroying crops with little warning. Farmers develop rapid cycle varieties that reach maturity in weeks rather than months, allowing multiple plantings per year and reducing exposure to any single storm. Greenhouses proliferate, providing protected environments where crops can grow regardless of external conditions. But these aren't traditional greenhouses. They're reinforced structures designed to withstand hurricane-force winds. They're transparent panels made from materials that flex rather than shatter, their foundations anchored to withstand winds that would tear apart conventional buildings. Vertical farming, growing crops in stacked layers inside buildings, expands from niche technology to mainstream agriculture. Vertical farms exist completely independent of weather, their environments controlled precisely. They're expensive to build and operate, but they're storm-proof and can be located in regions far from traditional agricultural zones. The transformation means less dependence on specific geographic regions for food production, but it also means agriculture becomes more energy-intensive, requiring power for lighting, temperature control, water circulation. The energy must come from sources that continue functioning through storms, pushing development of distributed renewable systems that can operate off-grid for extended periods. By 2050, half of global food production comes from controlled environment, agriculture, greenhouses, vertical farms, aquaculture facilities. Traditional open-field farming persists, but is concentrated in regions where climate remains relatively stable. The transition changes not just where food is grown, but what foods dominate. Crops that thrive in controlled environments become staples, while those requiring open fields become luxury items. Ocean chemistry changes as storms inject salt spray and atmospheric gases into marine ecosystems. Each hypercane carries millions of tons of ocean water into the atmosphere as spray, then deposits it hundreds of miles inland. The process removes salt from oceans and deposits it on land, where it eventually washes back through rivers, but the cycle takes months or years, during which regional ocean salinity drops measurably. Lower salinity affects marine life. Species adapted to specific salinity ranges must migrate to find optimal conditions. Coral reefs already stressed by warming and acidification experience additional stress from salinity fluctuations. Some coral communities collapse entirely. Others adapt, developing tolerance ranges that previous generations didn't possess. But the changes also create opportunities. Reduced salinity in coastal waters allows some freshwater species to extend their ranges into environments they couldn't previously inhabit. Estuaries expand, creating new habitat for species that thrive in brackish conditions. Ecosystem boundaries shift, creating novel communities that have no historical precedent. Nutrient redistribution proves equally significant. Storms mixing deep water bring nutrients from the abyss to the surface, triggering plankton blooms that alter food webs from bottom to top. The blooms increase ocean productivity temporarily, but they also consume oxygen, creating dead zones where most marine life can't survive. By 2050, ocean chemistry varies more from year to year than it has at any time in human history. Marine ecosystems exist in continuous disequilibrium, constantly adjusting to conditions altered by the most recent storm. Species that can adapt quickly thrive. Those that require stability decline. We're witnessing evolution at observable timescales, with storms acting as primary selective pressures determining which species persist and which vanish. The question future generations will ask, why didn't we act sooner? They'll study this era, the early 21st century, when climate change was recognized, but responses remained inadequate. They'll analyze decisions made, opportunities missed, warnings ignored. They'll judge harshly, but they'll also recognize something we can't fully appreciate yet, that the transformation we're experiencing might be necessary for long-term survival. That the disruption, as painful as it is, forces innovations that wouldn't occur during stable times. That necessity truly is the mother of invention, and the necessity created by hypercanes drives invention at unprecedented rates. Technologies developed to survive storm seasons find applications elsewhere. Engineering that protects against 200-mile-per-hour winds also protects against other extreme conditions. Early warning systems that detect hurricanes days in advance work for other hazards. The adaptive capacity developed responding to climate extremes makes civilization more resilient generally. Future generations might conclude that this difficult transition period, when storms like Milton became routine, was when humanity learned the flexibility required to persist on a planet where stability is temporary and change is constant. Or they might conclude we were simply lucky to survive our own short-sightedness. The verdict remains decades away. Milton's legacy extends far beyond the immediate destruction it caused in October 2024. The storm demonstrated that intensity barriers we thought were hard limits are actually permeable. It showed that hurricanes can organize in ways that make them dramatically more efficient at converting thermal energy to wind. It revealed coupling between atmospheric, oceanic, and geological systems that we didn't know existed. Most significantly, it proved that the future we feared was already present. We didn't need to wait decades to see what climate change would bring. Milton brought it to us, compressed into 18 hours of rapid intensification and 6 hours of catastrophic impact. The storm was a message from tomorrow, a preview of the new normal, a demonstration that the monsters we expected to arrive gradually were already here, fully formed, operating under principles we're only beginning to understand. We received the message. The question is whether we'll respond with the urgency it demands. The coming tempest isn't one storm. It's a transformation of Earth's atmospheric behavior, a shift into a regime where hypercanes become features rather than anomalies. The transformation is occurring now, in our time, during our watch. We can't prevent it. The thermal energy is already in the ocean. The atmospheric changes are already underway. Even aggressive mitigation, immediately reducing emissions to zero, wouldn't reverse momentum that's been building for decades. But we can adapt. We can build cities that survive Category 6 winds. We can develop agriculture that functions despite disrupted rainfall. We can create early warning systems that provide time to evacuate. We can engineer solutions that allow civilization to persist in a world where Milton-class storms strike regularly. The question isn't whether we can adapt. Humans are remarkably adaptive. We've survived ice ages and droughts, plagues and famines, wars and disasters. We'll survive hypercanes. The question is, what will we become in the process? Will we become more ingenious, developing technologies and strategies that previous generations never imagined? Will we become more cooperative, recognizing that climate extremes require collaboration at unprecedented scales? Will we become more resilient, learning to absorb disruption without losing essential capabilities? Or will we become more fractured, with resources going to those who can afford protection while others are left vulnerable? Will we become more desperate, as competition for safe locations and adequate resources intensifies? Will we become more accepting of loss, as repeated disasters numb our capacity for empathy? These outcomes aren't predetermined. They depend on choices, individual choices about where to live and how to prepare, community choices about investments and priorities, national choices about policies and resources, global choices about cooperation and coordination. Milton gave us a glimpse of one possible future, a future where storms routinely achieve intensities that were once theoretical, a future where coastal living requires constant vigilance and periodic evacuation, a future where hurricanes aren't just weather events but fundamental shapers of civilization. That future is arriving whether we prepare for it or not. The coming tempest has already begun. It started on October 9th, 2024, when a storm taught us that the boundaries of the possible had shifted, when a storm showed us that nature operates on scales we're only beginning to comprehend, when a storm demonstrated that the world we knew was becoming the world we fear. But it also showed us something else, that even at the edge of chaos, structure emerges, that even in the most violent conditions, patterns appear. That nature doesn't just destroy, it reorganizes, creating new configurations from the destruction of old ones. Milton wasn't just a monster. It was also a teacher, revealing principles we didn't know and connections we hadn't seen. It showed us that the atmosphere and ocean and earth are more coupled than we imagined, that storms communicate across planetary distances, that animals sense conditions we can't measure, that feedback loops connect present and future in ways our models don't capture. The knowledge won't prevent future storms, but it might help us survive them with our civilization, our technology, our humanity intact. The monsters are waking. They were always there, dormant in the physics of atmosphere and ocean, waiting for conditions that would call them forth. We've created those conditions. The monsters are ours. Now we must learn to live with them or decide whether living alongside monsters is possible at all. October 9th, 2024. The day the future arrived ahead of schedule. The day we learned that tomorrow's storms are already here, and that the coming tempest isn't approaching, it has already begun.